there. Okay, yes. Oh, and I'm live.
Okay, shall we get started? Great. Welcome everyone to the first workshop on the implementation of type systems. So to give some context, this workshop has been created to bring language designers together for collaboration, for discussions. And as such, we have a diverse set of talks today, again, each allocated with a generous amount of time for questions. So yeah, feel free to go further into details, discussion. Don't limit yourself to one-shot questions, and let's maybe see many other hands in the air at the same time. We also have, as you might have seen in the program, some slots later today without a scheduled talk, so that we can go even further into discussion and other forms of collaboration. So I'll say more about that when we get there. But yeah, if you already have topics in mind that you would love to talk about in this crowd, please keep them in mind for then. Okay, so without further ado, it's my great pleasure to introduce our invited speaker for today, Richard Eisenberg, who created WITS in the first place together with Jesper Cox in 2022. And when not creating new workshops, Richard is a language designer and compiler engineer at Chain Street, working on OCaml, as well as furthering his contributions on Haskell and GHC that I'm sure he's well known for with many people in this room. Before that, he's been a principal researcher at Tweak and an assistant professor at Bryn Mawr, after completing his PhD under Stephanie Weirick in 2016. Okay, so take it away.
Okay, thanks for that introduction, Sebastian, and for organizing the workshop today. First thing I want to say is this is meant to be sort of an interactive talk where we're not a very big crowd here, and I would love questions as we go. The whole point here is for everyone to learn something new, and you learn best by sort of asking questions and interacting. So please do feel free to raise your hand. So thanks for coming this morning. I want to talk a little bit about levels. Type checker level. Actually, let me just sort of poll the audience a little bit. How many people know what a type checker level is? Okay, I was actually expecting some more hands than that, although this does start from the beginning, but I was a little worried that like the whole first part was going to feel very, very boring, but I'm glad that I don't think it will. Levels are an implementation technique for doing type, sort of Hindley-Milner style type inference. And both GHC and OCaml compilers use levels, but then having implemented them, having used these for generalization, actually both compilers have found other seemingly unrelated uses. I mean, they're not unrelated uses, but uses that probably would not have been anticipated in advance. And so we're going to sort of explore a little bit of that this morning. So this is an old idea. There's nothing in this talk that's meant to be new or sort of my contribution, right? This is sort of a summary of stuff that's out there. Is there anything in this talk that I actually implemented? I don't think so. So this was first articulated in a technical report by Didier Remy in 1992, where he called them ranks, but the sort of standard term of art now is levels. And so what this talk is going to do is introduce them, and then I'll go through a couple of examples of how they get used in the OCaml compiler, and then a couple of examples of how they get used in the GHC compiler with little bits of code snippets every now and then. I have the code for both compilers on my machine. If we want to sort of explore that a little bit, if you have questions, we can do that. Okay, so this all starts thinking about generalization. This is sort of where it all begins. That we have a definition like this, and in this part of the talk, I use some sort of awful hybrid syntax between OCaml and Haskell, where they're different. So here, if we define the identity function, we don't know what the type of x should be. And so we're going to invent a fresh unification variable. So I'm using a convention in this talk where I put sort of types for things as a little subscript after the thing. So we'll see that quite a bit here. And so we don't know what the type of x should be. So we say, it's going to be some unification variable. So this alpha, right, this stands for some as yet unknown type that we're going to figure out as we're in the process of type inference. So once I assign that to the binding site for X, I can then label the usage site. And at this point, we're done, right? This is a very simple definition. And so we can now assign a type to id. So here I've taken advantage of the fact that this is not a recursive definition, and I just sort of give the type to id at the very end. If it was recursive, I'd have to do something else. But I don't think there's anything recursive in this talk. And so here we're done. So it's the argument is alpha, the result is alpha, and then we have nothing more to say about id, so we can generalize this to get a polytype that quantifies over A. So one thing, actually, I think one more there. A couple of other things to notice. So there's a number of sort of notational conventions that I'm bringing in here. So the first is that, as I said, we put the type sort of as a little subscript after terms. The next is I'm using Greek letters like alpha to refer to these unification variables, right? These are little constructs that we would have in an implementation, probably implemented by a mutable cell. Both GHC and OCaml do use mutable cells for this. Although you could imagine not using mutation and just building up a substitution on the side. That would work too. But they stand for some as yet unknown type, as opposed to Latin letters like A, which are sort of proper type variables that you would see in type theory. Right? This A here is a quantified type variable that, when we instantiate that polytype, gets turned into some other type. So there's sort of a slightly different class of thing. The other convention that I'm bringing in here is that I use purple for things that are in the process of inference, green for things that are done being inferred. And that's going to be sort of a bit of a squishy notion for much of the talk, and then I'll actually sort of come back later in the talk and define that a little bit more precisely. OK, let's look at a slightly more advanced example. Here we have swub, which does not, which sort of just X gets passed through right away. And Y, on the other hand, we call not on Y, so that's going to affect our type inference. OK, so I'm going to need a little bit more room here. So let's move things around. This is the same function. I just made more room. So just as before, we're going to say we don't know the types of these parameters here. So we're going to just assign them fresh Greek letters. And then we're going to label the recurrences. And now, as we type check the function, well, we first see X, its type is alpha. Then we get to not. And so we look up not's type, and not is going to have type bool, arrow, bool. So again, this is written in green here because we know the type of not. We don't have to do any work to find it. We just look it up. And then we see that the argument to not is this variable y. So it's not going to be beta anymore, but we're going to unify that beta with bool. And it is meant to be purple here. That's, again, a detail I'm going to come back to later in the talk, why I've labeled that in purple. And then we're sort of done inside the tuple. We can give the tuple itself a type of alpha cross bool, right? The bool coming from the result of the not. And then we can say what the type of swub is it has to be alpha to bool, the two parameters, as well, and then a return of alpha cross bool. When we've done all of that, now there's nothing more to do. And so we can generalize that type and get this polytype. Yes, Vivonia.
So what's the meaning of swap with this word?
Nothing. It's just a dummy word. Just felt like not writing foo. OK. Yes, Sam.
Well, when you used not, it was clear what its type was. But if you used ID, would you have also put the type in green at that point?
So if I'd used ID, there's some implementation details here. One possibility would be that I would change the A's to alphas, and they would be purple, but the arrow itself could still be green. Or we could change the arrow also to be purple, and that's the slightly different characteristics of those two type systems. Again, more about that sort of in the OCaml section, which really leans on that. Yeah, Cyrus?
So you got rid of the beta there immediately when kind of discovering that it was bool. If there were a future kind of inconsistent use of y, if there were an error there, is it okay to kind of solve it as you go like this, or do you want to keep constraints separately?
That's a great question. So in this example, I'm just going to summarize the question. So in this example, when beta sort of hit bool, right, we immediately unified beta with bool. But that means that if there was a type error later, we would we sort of have predisposed ourselves to think that that parameter has type bool, and then a later error would sort of report as if we always knew that y had bool all along. An alternative would be not to do that and instead build up constraints, and then you could have constraints sort of get solved later. That would work fine. So OCaml does all unification like that eagerly. It has no way of deferring constraints. GHC actually has both. So in GHC, if there's sort of nothing stopping it from unifying the beta with bool, it will do that eagerly and then sort of bias itself in type errors. But sometimes, if there's like a type family involved or something, GHC gets skittish and it won't do that. And then it delays to a constraint solver. And so maybe can produce better errors there. And actually, it's sort of an experiment that Simon and I have been wondering about performing, about just turning off the eager unifier and doing everything delayed, which would hopefully just work. Other questions? OK. OK. To really motivate levels, we need an even more complicated example. But now, hopefully, we're sort of understanding my notational conventions and how all of this works. So we have frob here. So just let's look at this for a sec, because in a moment, I'm going to split this up, and then it becomes much harder to read. So it takes these two parameters, x and w. Then there's a local function mook, which builds this result. And sort of a key detail here is that this x from out here and the y from in here end up in a list together. So those are going to have the same type. And then z just sort of gets passed through. I should say right now, this is meant to be a type correct function. So we're not looking for any errors here. And then I can call mook at two different types, right? Because I can generalize with respect to z here. So this is our situation. Yeah, William. Oh, this is a character z, yes. Yes, sorry, maybe that was poor choice because it could be confusing with the variable. No, it's just, I just wanted a character there. OK, so let's make some room. And we're going to start by labeling our parameters here. Again, with Greek letters, the only reason this is delta and not beta is that I ended up editing the slide later, and it's hard to change these later. So there's no semantic interesting thing about the fact that I'm not using sequential letters there. And then I've labeled the occurrences. Then the first thing I hit as I do type inference is this mook. But again, it not being recursive, I can just jump right into the parameters and label them with unification variables beta and gamma, and label the occurrences. Then the next thing I see is this list over here. And in this list, we see that we have to unify the alpha and the beta. And so here I've chosen to set beta to alpha, but I could have done it the other way around. And then at this point, the list itself is well typed, so I can give a type to the list. So that's a list of alpha. And let's see, what's the next step? Oh, then we're going to figure out the type of the tuple here. So this is just a list of alpha cross that gamma right there. And then now we have enough to get the type of mook itself. So we can see its two parameters, alpha and gamma. And then we're done with this let definition. So we're going to generalize. And so we get for all a, b, excuse me, a to b, the list of a cross b. And now we're going to use that down here in the two occurrences of mook. So when we do that, we take that polytype and we have to instantiate it. Because at this point, we don't know. We have these two polymorphic arguments here, a and b. We don't know what they're going to be at this occurrence of mook. And so we instantiate them with fresh unification variables, epsilon and zeta. And so this is something of an answer to Sam's question earlier of what happens when you have a polytype and then use it. And so here we're going to apply mook to w. W has type delta, so we're going to change that epsilon to be delta. Then we look up the type of 3 and discover that it's int, which I'm just abbreviating to I for space. And so that zeta becomes I. And then we do the same thing for the other use of mook. First, we instantiate it with fresh unification variables eta and theta. Unify the eta with the delta. Look up the z to see that it has type char. And then unify the theta with char. And then we're done with the whole right-hand side of frob here. And so we can give a type to frob, reading off the two arguments, and then the result. But something very strange has happened here. Yes, maybe you're about to ask about the strange thing. No. Oh,
Can you go back one?
not easily. but
Oh
I can
no!
do
Oh,
it.
sorry.
I can do it not easily.
Get to the when make has an inferred type with the for all. Yeah. Okay. So the alpha in the make is also the
Yes.
same as the alpha on the x and is this the weird thing? Okay, because I'm asking about why is there a for all a in the make? Yeah. Okay.
That's a great question,
Great.
and that's where we're going. That's
Okay.
sort of leading folks down the garden path, but making a mistake on purpose.
This is just I guess an implementation detail, but specifically when does the type checker decide to generalize? Is it whenever it finishes any let definition?
Yep. I mean, there are other points too, but that's sort of the canonical moment is at the end of a let definition. Yes. Jan, did you have a question? Or, okay, sure. Okay, let me forward through these other transitions here. Okay, so that sort of, as we were watching it, we had this type of MOOC with several unification variables that got generalized. But the type that we got here is wrong. Because it says that the two parameters to frob can have different types, right? This alpha and this delta here are unrelated. And yet, that x and w, sort of through these calls to MOOC, end up in a list together. And so they have to have the same type. So somehow we've done something wrong. And the lesson here is that we can't generalize variables that are already in scope, right? When we were generalizing the type of MOOC, there was that alpha, but that alpha sort of came from an outer scope, and we can't generalize it sort of locally once it's already been defined. So let's go back to the point that we made the mistake here. And so here, we're about to generalize this type of MOOC. But what I'm going to do now is I'm going to label these unification variables with levels. So this is a talk about levels, and we haven't seen them yet. Here they are. So I'm going to use a convention here where I label things with levels by using sort of a colon and a number. And so when we're at the top level, that's level 1. So we see that these outer variables here are level 1. When we're at the inner level here, the parameters of MOOC, these unification variables are at level 2. So there was that beta that was here on y at one point. That would have also been level 2. But sort of at this point in the evolution, we've already gotten rid of that, so we don't see it. And just again, for sort of space and to reduce clutter, I'm only putting these levels at the point of introduction of these variables. But you can think of this level as sort of being attached to that variable and sort of being carried throughout, right? But it's attached to the type, the unification variable, not like x or w. It's definitely attached to the alpha or the delta. Yes, Stephanie.
To be clear, when you unify two variables that have different levels, you get the smaller level.
You do get the smaller level when you unify two variables. That's covered more explicitly later, but yes, that definitely happens.
Is there a reason why you've chosen to number the levels this way rather than the other way? So, I mean, 1 could be 2 and 2 could be 1.
So you're saying starting at the top and then counting down. I think that would probably, I mean, there's no, I think that would be fine. You just have to sort of change the
I guess
list.
you'd have to shift them every time you
Oh.
encounter a...
Oh, I was just thinking start at a very big number and count down.
Right, yeah.
But, or, yeah, I don't think you would really have to shift them as long as you allowed yourself to go negative or something. Yeah. Okay. I appreciate all the questions. This is great. Okay, so here, so I've labeled these with different levels. And now the rule for generalization is that at any point in our syntax, we're at a certain level, right? The reason that this is level 2 is because I'm sort of in a syntax node within frob. And that's what's pushed me to level 2. It's a very syntactic sort of, it's just, you can just look at the abstract syntax tree and then know what level you're at. There's not further analysis needed. And so when we're generalizing the type of something that's at level 2, we're only going to generalize level 2 unification variables. So in this case, that's the gamma, but not the alpha. So when we generalize, we're going to get this type for all b, alpha to b to list of alpha cross b. And I could have just used a, right, because a is different than alpha, but it's a little confusing to have a and alpha next to each other, so I didn't do that. Okay, so now we can play the rest of this out much the same way that we did last time. now here, the type of MOOC at its usage site, it keeps the same alpha that we had before, because that hasn't been generalized. But this b, which was generalized, now we have to instantiate to a fresh unification variable epsilon. Now we end up unifying that alpha with this delta here. And so we're just going to unify the delta to become alpha. These variables were at the same level. I could have gone the other way, and everything would have been just fine, sort of arbitrary choice. And then once again, we look up the type of 3, and then unify. And then we do the same thing for the other occurrence of MOOC here. Here we don't have the alpha and the alpha already matched, so there's no step to take there. Look up the character z, has type char, unify, and then get this not yet generalized type for frob. But now we can generalize, and we get this nice type that is correct. Yes, Favonia.
For the purpose of the current algorithm, is there a level for zeta or epsilon?
Oh, yes, there are. That's a great question. I probably should have labeled them. They don't come into play in this, like there's no interesting interactions that happen with those levels, but an implementation would have levels on them. They would be at level 1 because they're sort of outside of, they're within frob, but they're not in another let definition within frob. Joe.
So the results of generalization are sort of, the internal results of generalization are no longer like actual normal prenex polymorphic types. They sort of have both like Latin type variables and so is it like always true that at level, like the only time that you necessarily only get prenex polymorphic types is at level 1?
So that's a good question. I mean, I would say it is still a prenex type. It's not sort of normal in that it has these unifications. It has exotic members or something like that. But the quantification still is up at the front. At the outermost level, you might think that you always have normal prenex things, but you don't in either language that we're looking at today, because OCaml has the value restriction and Haskell has the monomorphism restriction, and both of those can cause these unification variables to leak to the outer level and sort of essentially have level 0. Which is strange. In both languages, this feature is strange, but it exists. William.
OK, so let me just, I feel like I'm missing something because this seems incredibly obvious, but it sounds like what you're saying is you are labeling each scope with a level, and then you are only generalizing within the same scope, kind of out, inside out.
Yes.
OK.
Yep, that's it. And there, oh, yeah.
Hi, a Stephen question. So why did I and C up here are purple instead of green?
That's a great question. I want to defer the answer to that a little bit later.
Right,
in the OCaml section, I'll cover that. And there was another question, I think, over here. No, OK. OK. Great. I think we're done with that example, I hope. Yes, OK. So, so here I've explained all of this using levels, but there's another way that people might have encountered this. It's just sort of looking for free variables in the context. So here's a screenshot from the paper on mini-ML from 1986 that is sort of the first time that this I saw, at least, written out in a nice typing rule. This is actually, it's not a fresh idea in this paper, but it's a nice way of describing the idea. This comes from Damas and Milner originally. But what's going on here is that here's the rule for let generalization. The reason that there's a bunch of the reason that it's primed is because this is the sort of syntax-directed version of the type system written in the paper, as opposed to the sort of specification of the type system, which is elsewhere. So in here, we type check this expression E, and then we get its type tau prime. And then the type that we add to the environment is not tau prime directly, but this type sigma. And where sigma is the result of generalizing tau prime with respect to the context A. That definition is just down here. And so it looks at the difference in the set of free variables in tau and removes all of those free variables that are also in any type in the context A. And the problem with this works, but something was supposed to happen. There we go. But right here, this can be slow. right? If A is big, we have to look through a lot of things looking to see where what the free type variables are, and then we have to do a set difference, right? And so levels are basically just another way of performing this same operation by labeling where the variables were invented. But I just wanted to sort of relate this back. I mean, this presentation that we see here is sort of the common one that most textbooks would describe as this is how you do let generalization. I'm not deviating from that. I'm just sort of being a little bit more efficient. Okay. There's another interesting observation that I'd like to make at this point. So there's an excellent blog post by Oleg Kyzylyov explaining how all of this works, going through lots of examples, toy implementations, highly recommended, and relating this idea of sort of using levels as a way of sort of thinking about essentially frames and garbage collection. And I'm not going to try to summarize that here, but I do recommend looking at that article. There's no date on here because it's just sort of a blog post, and I don't know exactly when it was written, but it was not. The most recent edit was in 2022, but I know it was not written in 2022. Okay, so that's this first part. So now we know that this is the fundamental idea about levels. But I want to now dive in and talk about how they work in OCaml, and then we'll come back and look at them in GHC. But before I can even talk about levels in OCaml, I have to explain a little bit about how types work in OCaml. Maybe this is just because my experience was in GHC before seeing the OCaml type checker, but I personally find the OCaml type checker to be have an interesting approach toward representing types, and so we sort of take a small digression into how that works. So here are the actual definitions from the OCaml compiler. When we see code that looks like this, they are screenshots from the actual compiler code, maybe with tiny edits for formatting or something like that. So here, let's just completely ignore transient expr. That's not the interesting thing here. Instead, we'll just pretend that this transient expr is type expr. But in this type, we have a couple of fields, one of which is type desc. Type desc is down here. And type desc sort of describes the algebra of types, right? This is sort of the data type, at least that I would first think of as, oh, this is the real data type in the compiler. And then we can have variables, and we can have functions, and I've cut off tuple there to sort of suggest that there's a bunch more down here that I'm not going to put up on the slide. But this type desc is recursive with type expr up here, not with itself, right? So here, inside of a function type, what we have is we have further type exprs that have this extra information up there. So the first thing I want to sort of look at is that in a variable, right, I would naively expect some kind of unique identifier for the variable, not just its name. And the name is even optional. In OCaml, all of these unification variables that we've been seeing, they're actually represented with none here because the user didn't write the name, so we don't have a name to give it, so we just give it none. And so the way that we tell that two variables are the same is by pointer equality on the type expr. So the type expr, as you saw, has mutable fields, and so that means that pointer equality is a well-defined notion on type exprs. And so if I have one tvar here and one tvar there, and I want to know are they the same variable, I have to sort of zoom out one level, find the type expr, and then use pointer equality. And I mean that's a unique identifier. This works. At least for me as a type system implementer, when I first came across this was quite surprising. But that's how tvars work here. Then the next thing I want to look at is that the level, as I presented it earlier, a level was something that was associated with a unification variable. And so I would expect it to be on a tvar, but it's not. Instead, every expression has a level, and in fact, those are mutable. So I'm going to talk about those two details in the next couple of slides. But again, when I first came across this was quite surprising to me. So the first question is, what does it even mean to have a level on a type, right? When it's these type variables, these unification variables that seem to want to have levels. And so here I've switched now to actually using proper OCaml syntax. And so if I have a type that looks like this, that type really only makes sense at level 2 or greater, right? If this type somehow flowed out and was the type of a variable at level 1 outside of that bit of the syntax tree, this level 2 just doesn't make any sense. I don't know what that would mean. And so if I want to assign a level to the entire type, it's just the max of the levels of its variables. And so that gives us at least a semantic idea of what it could mean for a type to have a level. As it turns out in OCaml, this is not necessarily a tight bound. But as long as it's at least the max of its levels of its vars, then that's fine. So we're always going to have an invariant that actually the level on a type is greater than or equal to the levels of all of its, well, not just variables, but components, right? Because each type going down the tree has one of these levels. OK, so now we understand sort of how a whole type can have a level. Why are they mutable? And that's because in OCaml, types are not trees. I always like to think of types as trees, but in OCaml they are graphs. OCaml supports recursive types, and I don't just mean, so in something like Haskell, Haskell has recursive types, but there's always a type constructor that sort of mediates, and then you can look up that type constructor, and the structure in memory is still just a tree. But in OCaml, they're really graphs. In the object system in OCaml, you can end up with types that contain themselves, and also there's the rec types flag to OCaml that allows you to even create tuples that contain themselves. And so when you have graphs, now suddenly pointer equality becomes more interesting, and copying these things becomes harder. And anyway, before, as I said, variables are known by their pointer location. So we don't want to just sort of copy types unnecessarily, right? That wouldn't just be inefficient, it would be wrong, and it would break type inference. And unification and generalization operations can change the level. So we really need to mutate those levels in place. Otherwise, the language wouldn't work, or this particular implementation wouldn't work. OK, so we have these mutable levels on types. In OCaml, when we infer the type alpha at level 1 goes to alpha at level 1, that just generalizes to this type here, where both alphas are now at level infinity. But I've missed one small detail. Of course, types have levels, not just unification variables. So the first type might be itself at level 1, and then the second one, this type is also going to be at level infinity. And we need to change the whole type to level infinity as we generalize, because otherwise we would violate that invariant that the level on a type always has to be greater than its components. Yes?
Why is it level infinity and not level 0? Because I thought you said earlier that a type only makes sense at a level that's greater than like all the maximum of all the things inside of it. So if infinity is larger than everything, how does this make sense as a generalization?
So that's a great question. And in practice, in the OCaml type checker, there's a number of places that do a level comparison, but have a special case in case it's infinity, sort of to deal with that. It is pretty good to use infinity for this, but not perfect. The other way to think about it, though, is, as Stephanie pointed out earlier, we lower levels, but we sort of never raise them. In that this type makes sense sort of at all contexts. And so if we want to use it at level 15, that's fine. We can put it in at level 15 and then change the alphas to be at level 15, whereas that wouldn't really make sense to raise them. So in that way, it works really well to have it at level infinity.
How do you represent the level infinity in the type?
That's a great question, and just hold on to that for about 5 seconds or so. OK, only generic type can contain generic variables. Then, great question, how do we represent infinity? Infinity is actually 100 million. And so this again, this is real code from the OCaml type checker. And infinity really is just 100 million. Because for reasons that I have not yet explored, it needs to be less than 2 to the 27. And I did check as I was preparing this. 2 to the 27 is indeed greater than 100 million by a bit. And so if you were to somehow write an OCaml program that had more than 100 million nested scopes, I'm sure you'd get some very strange behavior, but you'd run out of memory first. So I think in practice this is fine, but it's just a little sad. OK, so that's how that's represented. And then actually there's a couple of places in the type checker where things have to be plus or minus by 1. So every now and then we take this and add 1 to it to make it even more generic, or subtract 1 to sort of protect it from being generic. Very strange stuff. The other interesting thing here is that there is no for all. So when I took that type and generalized it, in the examples at the beginning of the talk, I added a for all A. But I have not done that here. And that's because OCaml does not, or rather, the way that OCaml represents sort of generalized variables as opposed to unification variables is just by their level. That's the way that we recognize the difference. There's no explicit quantification. Yes? Go for it.
They kind of have universal quantifier in OCaml, type A, blah, blah. When you do that, they assign the level there, or does it do something different?
So it depends on where you do that. In like if you say like let f colon like tick a dot, and then that's a way of saying that. Actually, the OCaml type checker at first ignores that, does full type inference for the thing, and then checks to make sure that that particular variable got generalized. In other contexts, it will create something. The OCaml type checker does actually have a notion of a generalized variable that's different from a unification variable, but it's not used very much. And so I can't remember which construct causes that to come into play. No, type A blah, blah, blah doesn't do that. Type A actually gets desugared in the parser to the tick A dot plus a type A somewhere else. I think maybe it's in record fields that have quantification that use the proper one. It does exist in the type checker, but it's not the thing that relates to this talk. Yeah, Sam. Yeah.
Clarifying that again. You're saying that by default, OCaml, the OCaml implementation has no notion of an object level type variable.
That's right.
It only ever has unification variables, just some of them have level of infinity.
Yes,
Right.
yeah, that's right. Yeah.
I have to get back to that 100 million for a sec.
Yep.
So I can see that it's a practical solution, maybe even simplifies some code, but do you also know of bugs that may have caused, especially around that ±1?
I mean, around the plus and minus one, yes, but if we had some other representation for generic level, I think the plus or minus, I think those bugs would have existed regardless of the use of a specific number. No, actually, I don't know of specific bugs that are caused by that, because 100 million is a lot bigger than 1 and 2.
That's true, yeah.
And even in a complex OCaml program, you're not going to get more than 10 or so. I mean, it's
sure.
You don't.
But like, if it had been, say, a separate constructor, then it would not be possible to accidentally increment it.
That's true, but I think that the code that does that would actually be significantly more complicated than the way that it's currently written.
Makes sense.
It's like the way that it's currently written. When you first look at it, you kind of don't know what's going on, but then you read a description of it and it makes good sense. And I think it's somewhat simpler implementation than it would be otherwise, actually. Okay. So the only way that we know about these sort of generalized variables is by their level. And so that means that when we take like the example that we saw with Mook, when we used that, we then had to sort of instantiate the quantified variables. The way that happens in OCaml is by using this instance function, which takes a copy of a type and changes all of its generic parts to be at the current level. Right, so remember, at every point in time, I didn't really push this point earlier, but at every point in time, we sort of know what level we're at. Right, we know how deep in the abstract syntax tree we're sitting, and so this instance function, every time we sort of look up a type, we have to call instance on it to bring it down to the correct level. Okay, and the other important thing here actually with instance is that it also makes a copy of the type. So that way, as we're doing unification on it, we don't want to edit the master copy of Mook's type. We just want to edit the particular copy that's being used here. So the copy part is important. Okay. Yes?
How does that interact with the pointer equality that you mentioned?
Yeah, so how does that interact with the pointer equality? So Generic variables, when we do that copy, will get copied, but we want them to be copied because any changes that we make to the generalized variables, we don't want to affect the master copy. The non-generalized variables don't need to get copied because of this. So as we're doing that copy, as soon as we find a type whose level is less than infinity, we don't copy that part, which is both an optimization, but also necessary for the reason that you just said.
I also have a question. What you said earlier, and you said that because the fields are mutable, the pointer equality is well defined. Would it not be the case? Should the field not be mutable?
So yes, if you look at the specification of pointer equality in OCaml, it is only well defined on types that have mutable components.
And has the behavior with pointer equality ever caused bugs? Like related question to earlier.
I mean, I don't. That's a good question. I don't know a good answer to that. I mean, that's like not specific to the OCaml implementation. I mean, this is just sort of a property of the language in that if you try to use pointer equality on immutable things, maybe it's been copied, maybe it's not.
I mean, in the type checker, I mean specifically.
No, I'm not familiar with that. It's again, it depends on what you mean by like, is that what's causing the bug, right? If you make an unnecessary copy of something, now that pointer equality fails, but the unnecessary copy is kind of the bug. It's not.
Fair enough.
Yeah, it's not the choice of pointer equality. Sure. Okay. Let's see, where are we going next? Yes. So, so here we have just sort of one more example. Here I want to talk about unification. I talked about generalization, and I want to cover unification. So if we have this function, we're again going to have to unify the type of x with int. And so I've split it up here and written it in prefix form so that we can do type inference. So as usual, we guess the type of x is going to be some unification variable alpha. I have not written the levels here because we don't have a lot of nesting, so I didn't bother with the levels on this one. And then we look up the type of plus to see that it's int, arrow, int, arrow, int. And we're going to have to unify alpha with int, and we get int. But here we get purple int instead of green int. And the reason for that is that when we unify the alpha with int, we have to take the level of int and lower it to the level of the alpha. And the reason that we do that is that we're actually still doing inference on x. And so this is sort of a quick explanation of what's going on whenever we've seen this in previous slides, that as we're doing unification, we always end up at the lower level of the two things being unified. That's always the property that we're going to have. But why do we do that? It's because we want to know the difference between what we're sure of and what we're inferring. And why do we want that? Here's an example. So in OCaml, declarations are ordered, unlike, say, in Haskell. So we can have two definitions like this, T1 and T2, where the A and B constructors of T2 will shadow the A and B constructors of T1. And this is not uncommon in OCaml code. In the definition of F1, we come across and we see, well, what is the return type of F1? Well, it has to be the same type on both branches of the if. And so we see the C first. So we know then that we're returning T1. And OCaml has this feature of type-based constructor disambiguation, which means that now that we know that we're returning T1, when we see B, we're not going to use T2's B. That's clearly wrong. We're going to use T1's B, even though T1's B is shadowed. And so F1 is accepted. And I'll get back to this warning in just a moment. In F2, on the other hand, we see B first. That's going to refer to T2's B, because that's the one that's in scope. And then when we see C, well, that's clearly the wrong type. And so we get a type error saying T1 does not equal T2. Of course, this is slightly sad, or maybe more than slightly sad. This is sad, because generally in type inference, we want not to care about what order we do type inference, right? It just so happens that we do the then branch before the else branch, but of course there's no principled reason to do it that way. And we would like to be able to design a language that we can swap these things the other way and still have our programs type check. And so for this reason, OCaml has a principal mode, which happens if you pass -principal when you're compiling. And in that case, it will warn on F1, saying that, oh, you know, the type-based disambiguation of B was done non-principally. How does it do that? It does that by noticing that here we invented a unification variable for the result of the conditional. And then when that unification variable unified with T1 after looking at C, that T1 got lowered down to level 1. And that meant that when we were trying to do the disambiguation on B, we could see that the type was at level 1, not level infinity. And because it was at level 1, we knew, this is just sort of the result of some inference that's still happening. We're not really sure. We should warn because maybe this is fragile. There are ways of getting a type at infinity. If I had put a type annotation, not on C, if I had put a type annotation sort of around the whole thing, then that type would have, there's sort of an exception in the way that the levels flow, and then that type would have stayed at level infinity, and then we would have known that the type-based disambiguation was reliable. So this is sort of one of these other extra features of levels that get used in OCaml, in that we can say something that's at level infinity is something that we sort of know solidly and that we can use in a reliable way for this disambiguation. Anything at level less than infinity, oh, this is still an inference. We're not quite sure yet. I saw some questions.
Maybe you don't know this, but has anybody looked to see how much code would break if you turn this warning into an error?
Oh, I mean, the compiler itself has this warning as an error. So in the compiler source code, I couldn't write F1. I know at Jane Street we do not use this principal mode because it actually slows the compiler down, not by much, but it's measurable to do these extra checks.
This didn't used to be allowed in OCaml. It's fairly recent, like OCaml 4 or so, I think.
Okay.
You were allowed to do this. So.
Okay, that's good to know. Okay, so I think that's the end of OCaml. Oh, yes, another question.
Yeah, really short one. When you pull in the types like of say it was plus before, like a top level function, are you receiving a fresh like mutable structure of the type of the like function or whatever?
Yeah, so that's a good question. So for a non-parameterized, for a type without any variables like plus,
okay,
we could get away without doing that call to instance. As it turns out, and I've sort of been a little loose with this in these slides and was a little worried that someone would call me on that, as you have. But actually, when we look up plus in practice, it would get lowered down to the current level in OCaml, because every time we sort of look up a type, we then instantiate that type, even if there's no variables in it, and change all of its levels down to the current level.
So every time you get it, it's like you're doing something new, kind of.
Yes.
Okay.
Yeah.
Thanks.
Okay. I think let's move on to GHC. Yes. So the generalization scheme that we saw at the beginning takes place in GHC, just like it does in OCaml, but of course the implementation is quite different. So here is the data type definition for TC level, TC standing for type checker. And this is not an int in GHC, but instead it's a data type that wraps an int. Interestingly, and only quite recently, as part of quick look, that's what the QL stands for, we've had to add infinity to this type in GHC also. But instead of using 100 million, we're actually just using a different constructor. And so the other thing that I've highlighted in the snippets of GHC code that I've shown here is there's quite a lot of comments in GHC and not quite so many comments in the OCaml source code. In any case, this QL inst var, I do wonder how this might relate more to OCaml, being that it's another way of standing for infinity, but for a totally different use than what OCaml does. And I have not thought closely about how these things might line up. But we're going to ignore QL inst var for this talk. So that's TC level. And then now we can look at the type structure in GHC, which is graph-like, which is tree-like, not graph-like. So we have the type, which has a bunch of other constructors that we don't see here, but this is the one that's interesting for us right now. It can contain vars. This is a var, which also has other constructors, which we're not going to look at right now. But it has a tick-tie var, so this is a type variable as it exists in the type checker, as opposed to a type variable as it exists in the core language of GHC. But again, we don't see that other case here. So here we have a name that might get printed out to the user, but this also has a unique. So we're not using pointer equality in GHC, but we're just, when we want to compare two variables, we just compare their uniques. It has a kind. This is the kind of the variable because Haskell is a higher kinded language. And a tick-tie var details, where this is the full definition of tick-tie var details. And it says that one of these tick-tie vars can be a scolum. This is something that's rigid. So this would be used to represent, for example, an existential variable that's been brought into scope. And it's also used to represent for all quantified variables when you have a type signature. Or we have a runtime unc, which we're not going to talk about. This is part of the GHCI debugger, which is a not very often used feature of GHC. Or it can be a meta TV down at the bottom. This is the, GHC calls unification variables meta variables. So this is the representation of these Greek letters that we've been seeing. So to very close approximation, scolum TV are Latin letters, as I've been using in this talk, and meta TV are Greek letters, as I've been using in this talk. Note that both scolums and meta TVs have TC levels. Right, that's how this all connects back to levels. And then a bunch of other stuff that we're not going to get into. OK, so types are trees, and levels are on variables, just sort of pulling out the points from the previous slide. So we don't have levels on types in GHC. And what that means is that, so in OCaml, when we have a generic type and we want to instantiate it, the parts that don't need to be instantiated, we can see that their level is sort of less than infinity and then stop. Right? And there might even be a large chunk of type that we can skip over and not worry about. GHC does not get that optimization. If I have a big type, there might be large regions of that type that have no variables that need to get instantiated, and we still have to walk over all of that and looking for these variables because we don't sort of have that cached information in the type. It's not clear to me. It might be a win for GHC to store levels on types the way that OCaml does. But then we're storing more information. Things get a little bigger. I don't know. It's an experiment that we could try. OK. So here in GHC, if we have this type up here, and now I'm still labeling the unification variables in purple, but we don't have this notion of what we know versus what we're inferring for anything other than unification variables. So I've made the arrow white there, sort of on purpose. Anyway, this generalizes to this polytype. So here, what we see is, I don't know, how many people here are familiar with inferred variables versus specified variables in Haskell? OK, not too many. That's probably a good thing. So Haskell allows you to use visible type application. And that means that we can purposefully instantiate certain type variables. But we don't want to do that for types that have been inferred because the order of the type variables is then squishy. And so for this inferred type, we put braces around it, which is actually syntax you can write in Haskell to prevent someone from being able to instantiate that variable. But that's what these braces are doing. Not all that important for this talk, but I wanted to get that detail right. And when we're doing this, so here we have the type in GHC again. So we saw tie var tie. There's also a for all tie, which stores a for all tie binder. And that's a representation of this A and its braces. Right? So there's several different flavors of binders and such, but it includes the name, and it includes sort of whether it's inferred or specified or a couple of other possibilities. And then the payload type. This is just a tiny snippet of code that actually constructs this thing. So there's a lot of code in GHC around generalization, and I needed to find something that I could put on the slide. So after we figured out the quantified type variables, the QTVs, and an inferred theta. Theta is the word in GHC used for sort of a set of class constraints that might get inferred on a function definition. And so we choose the correct inferred quantifiers, and then we call muk invis for all ties, which is just sort of a wrapper around this for all tie constructor. And so that's how we sort of construct this thing here. And then there must be a substitution that actually applies the binders. Maybe that's already been done in mono tie prime further up. OK, so that's how generalization happens. There's a key step. I wasn't sure how much time we would have. I don't think we have time to start sort of pouring through the GHC source code, but I'm happy to show that to you later. OK, unification in GHC. So here's a little example. We have an outer function and an inner function. And the key thing here is that the types of x and y are going to get unified when they end up in the same list. So x is going to get a unification variable alpha at level 1. Y will be beta at level 2. And then when we get here, we're going to have to unify. So we have this unification problem, alpha at level 1 against beta at level 2. And at first, it seems that we have two different choices of how we're going to unify these. Do we set beta to alpha, or do we set alpha to beta? But it turns out that this is not an arbitrary choice. Setting alpha to beta would be bad, right? Because beta is at level 2. So if we let that flow into alpha, then that means that a level 2 thing now can be seen at places where level 2 just doesn't make any sense. And so we don't want to do that, and instead we want to do this. And indeed, there is code specifically in GHC that sort of does this comparison and tries to show it to you. I wanted to get it on the slide, but like, there's not one crisp spot. There's instead hundreds of lines of code that do a lot of things, including this. And so that's all in unfilled var1, which again, I don't think we have time to sort of delve into right now. Another thing that GHC uses levels for is to check for Skolem escape. So this is one of these other things. Again, levels sort of starts out thinking about generalization, but here's another good usage. Actually, historically, levels first came in for Skolem escape in GHC, and only later got used for generalization, which I find sort of strange in the history, because we should have done it the first time. But so here we have sort of a pretty dumb existential type that just stores some unknown payload. This is not a useful type, but it's useful for an example. And this function f, which should not work, right? We shouldn't be able to return y. There's no type that I can give to f. So I'm just going to rewrite this slightly more explicitly, making for an explicit pattern match, and then give myself some space. So arg here is going to have a unification variable alpha at level 1. And then we go into the case. And the first step here is to say, well, I need some unification variable to represent the result of the case. And I'm just writing that as a subscript on the keyword case. And so that's going to be beta also at level 1. Then the next step is to notice that this scrutiny arg, that has to be of type x, ex. So I do that unification. Nothing interesting happens there. But then now, this y, that gets type a at level 2, not alpha, right? This is an existential, so it's going to be one of these Skolem variables. And as I said, I'm representing using Latin letters. And so now, when I figure out the result of this pattern match, I have to unify beta with a. And so again, I can think these are two variables. Which way am I going to unify? Am I going to unify beta equals a, or am I going to unify a equals beta? Well, this one's bad because my levels don't work out. As we saw before, I can't have a level 2 thing flow into a level 1 thing. So I'm definitely not going to set beta equals a. And this other one is also bad because a is a Skolem. It's not one of these things that I can fill in. This just doesn't even make sense. And so indeed, neither of these is going to happen, and I get a type error. And that's exactly the behavior that I want here. But this is done using this level check inside of GHC to sort of notice that this is going wrong. Yeah, Sam.
In the previous example, where you're unifying alpha and beta at different levels, you said, oh, one way is good and the other way is bad. It's actually fine if you set alpha to beta or beta to alpha, as long as you then change the level to be the lowest one.
Yep, that would also work. In practice, though, it does what the slide does. But we could do that. GHC calls that operation promotion. And so here, this is, I think, the last technical slide of the talk. When we are done with a construct, we must generalize, promote, or error. This is because these levels right? It's sort of how deep we are in the syntax tree. You could almost think of a level as some kind of approximation of a description of the path from the root of your program down to the particular point that you're in right now. But if you have multiple different local let definitions, right, those are still different places. They might both be at level 2, but we don't want variables to flow from one to the other. And so both compilers very carefully need to make sure that as soon as we're done with some local definition, nothing at level 2 remains. And so that means that there's constructs in both implementations that we either generalize, and that gets rid of all of the variables, promote, a word that I haven't really used before, which says that we take things at level 2 and sort of let them leak out to level 1, which sometimes does weird things with type inference. This is like the monomorphism restriction, the value restriction, but it still prevents us from doing crazy things, or just error and stop compiling. Okay, conclusion. Levels are a convenient mechanism in type inference. If you are implementing a type inference engine, you should use levels. This is the right way to do generalization. And when you do use levels, you will find other uses for them, as both of these compilers have. Thanks so much for your questions this whole time and for your attention.
We have time for maybe one more question. And otherwise, maybe I look into GHC could be an interesting collaboration time.
Yeah.
Yeah, it's a really excellent talk and very approachable. So you said a couple times in the talk that you're not doing any recursion. Do things change with recursion? How do they change, or no?
No, recursion doesn't pose too much of a problem. It just means that on a recursive definition, you invent a unification variable for the type of the function itself, so that at recursive occurrences, you know what it should be. And then through unification, it just sort of gets solved. It would just mean extra steps in the examples, but it doesn't pose any particular challenge.
Okay, I think we have to move forward. Let's thank the speaker again. And the next test. The next talk is a recorded talk towards generic higher order unification implementations in Haskell by Nikolai Kudasov.
And together with my collaborators, hello everyone, my name is Nikolai Kudasov, and together with my collaborators Artem Starikov, Fyodor Ivanov, and Damir Afletonov, we will present our work in progress on an approach to generic high-order unification implementations in Haskell. High-order unification is a process of solving symbolic equations with functional variables, and it is widely used in type checkers, interactive proof assistants, and high-order logic languages. As a simple example of its use in a dependent type checker, consider an identity type for two pairs. Now, since the identity type in Martin-Löf type theory is well-formed, well types on both of both pairs is the same, we have to check or infer and unify the types on both sides. In the case of dependent pairs, we will need to infer the type family, unless specified, that indicates the way that the type of the second component depends on the value of the first component in a pair. This can be reduced to a simple system of unification constraints, as you can see on the slide, to be solved by a high-order unification algorithm. Now, in the past 50 years, a multitude of high-order unification algorithms has been accumulated, both in the literature and in various implementations. U's pre-unification algorithm and Jensen and Pietrkowski's full high-order unification algorithms are perhaps the first and most well-known. Miller's high-order pattern unification limits the kind of unification problems that we're trying to solve to a decidable and unitary fragment that can be processed efficiently. For these reasons, variations of Miller's pattern unification is very popular, specifically in type checkers, including interactive proof assistants based on dependent type theories. Now, automated theorem provers, such as, for example, superposition, often require full high-order unification. And particularly, one of the recent papers by the team behind the superposition presents a combination of techniques dubbed full efficient high-order unification that makes this very efficient. That said, reusing these implementations is not really straightforward. The algorithms in the literature are often stated for a simply typed lambda calculus or a similarly minimal language, and implementations are often bound to a particular language or core language or a tool. To the best of our knowledge, none of the high-order unification algorithms are available as a library implementation that are ready to be reused by a developer of a new formal system. Now, this unfortunately forces developers of new tools or new formal systems to either learn and implement complicated high-order unification algorithms and also adapt them to their own language, or abandon user-friendly features in their tools, such as implicit arguments or type inference in their proof assistants.
One of the main inspirations for our project are generic libraries for first-order unification. In particular, the unification ID package implements such a library which follows Tim Short's function pair. In this library, syntax of terms is generated from a signature. It is a non-recursive data type which specifies possible syntactic constructions of the object language. Terms in this object language can then be recovered by taking a fixed point of the signature. Syntax for unification terms is generated similarly by injecting unification variables into the object language. Unification is then implemented in a generic function, parameterizing over the signature. Now, we would like to generalize this approach to higher-order unification. To do that, we need to figure out how to freely generate syntax with binders, and also how to account for semantic equivalence of terms. Setting aside implementation details for a moment, we rely on second-order abstract syntax. Just like generic unification terms, second-order abstract syntax is generated freely from signature. In this case, however, the signature also accounts for the binders. Each subterm of a syntactic construction is allowed to bind 0 or more variables. For example, function applications takes 2 subterms, both without binders. At the same time, lambda abstractions take 1 subterm, but with a single variable binder. Second-order abstract syntax also freely adds variables, but they are local and we do not normally consider them as unification variables. So we inject, in addition, second-order variables or meta variables. They are always parameterized with a list of terms. Meta variable substitution may only use these parameters to replace the meta variable. Although they may behave like functional variables, they cannot take other meta variables as inputs, and thus they are not higher order. Equipping second-order abstract syntax with equational logic, we get second-order equational logic, which we believe is a great framework to do higher-order unification in. Unlike higher-order abstract syntax, for example, second-order abstract syntax is much easier to work with. We also know that higher-order unification can be considered as a special case of equational unification for second-order abstract syntax, since equational theory of higher-order systems can be presented as a set of second-order equations. Parameterized metavariables also partially cover functional metavariables. And finally, we know how to present second-order abstract syntax in Haskell and mix it with the data types a la carte approach. Now, to make the things actually work, we need to select a proper representation of syntax binders and somehow adapt known higher-order unification algorithms to the second-order setting.
There are many possible ways to implement abstract syntax with binders. And here you can see a non-exhaustive list of representations. In our project, we want a representation that provides some kind of intrinsic scoping, efficiency, and compatibility with data types a la carte approach, or similar. At the moment, we are working with the free-foil approach, which is essentially a version of free monods with binders. Free-foil allows us to generate an efficient, intrinsically scoped abstract syntax with binders. Here, signature is given by data type with two type parameters. The scope parameter corresponds to subterms with exactly one binder, like body of a lambda abstraction or let binding. The term parameter corresponds to plain subterms, like the two subterms of a function application or the first subterm of a let binding. The type constructor AC is provided by the library and is akin to the fixed point combinator that automatically adds variables and binders in the correct places. The phantom type parameter n is statically tracking the scope of a term. This is a feature of an underlying foil approach, which is in turn a type safety mechanism on top of the rapier, an efficient implementation of the bar-indirect convention for bound variables, which is used by Glasgow Haskell compiler as well as Agda. Finally, the library implementation of FreeFoil provides convenient template Haskell helpers that work well with sparse generators like BNF converter, making it easy to develop prototypes for small object languages. To recover second-order abstract syntax, we need also to add parameterized metavariables. Instead of having them built in, currently we choose to rely on compatibility with data types a la carte approach and specify a separate signature for metavariables. The second-order abstract syntax is then generated freely from the sum of object language signature and metavariable signature.
So before moving on to higher order unification, we consider a much simpler problem of second-order matching. Matching refers to a subset of unification problems where unification variables, or metavariables, are located only on one side of each unification constraint. Since in our setting, metavariables are parameterized, matching is much more interesting than its first-order counterpart. Second-order matching is not unitary and it may produce multiple distinct solutions. It also partially covers higher-order unification and is useful in comparison of substitutions, but also requires some non-trivial techniques for an efficient implementation. Interestingly, second-order matching does not require fresh metavariable generation in our implementation. And we are at the beginning of our journey, and so far our main results are an implementation of the second-order matching via FreeFoil and a preliminary test specification for untyped higher-order unification problems. We are also working on generalizations of UE-style preunification and function as constructors higher-order pattern unification. However, both require a proper generalization of hereditary substitution, and the former also requires some generalization of UE-style projections. Talking about our future work, first, we plan to implement a higher-order unification benchmark suite to compare unification algorithms in isolation, rather than as a part of type checker or a theorem prover. This is somewhat a tangent goal, but we think it may be useful to a larger community. Second, we plan to implement at least a generalization of some basic unification algorithms, specifically UE preunification and Libel and Miller generalization to pattern unification. called functions as constructors higher order pattern unification. Third, we would also like to implement a somewhat useful application that would rely on our generic algorithms. For example, we think every implementation of talk may be interesting. And finally, there are, of course, many places for improvement and configuration, especially with respect to the performance of our generic implementation. In like particular meta variable representations, more precise control over laziness in Haskell, optimization techniques such as interning or fingerprint indexing should all be considered as potential improvements, of course, after we have a fully working prototype. And this is basically it. Thank you all for tuning in, and we will now be open for questions or comments on our work.
Okay. Great. Nikolai, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, perfect. Great. Other questions for the speakers? Okay, then let me start with one. So, yeah, you said the goal was to, of course, make it easier to bootstrap new languages, experiments perhaps as well. Also some toy language that you mentioned in the end. Yeah. So what do you think about scalability? Do you want to focus on these simpler applications, or do you see this also scale to yeah, arbitrarily complex compilers?
Thank you for the question. I think that at the current pace, at least, we're looking forward more into small systems and just being able to reproduce results and algorithms from papers and stuff like that. One maybe important block towards better scalability is the ability to work with the mutually recursive definitions. And I think that's the main one, I guess. And the only system that addresses that in some way that I've seen is hypertypes, but that's a slightly different approach, I guess, than what we are taking at the moment. So for now, we're choosing sort of to stick with the somewhat simpler free FOIL approach. Hopefully, we'll figure out how to make this truly scalable. But for now, we're looking mostly at fast prototyping, maybe, rather than developing large-scale systems.
Makes sense. Thanks. Other questions? Okay. Otherwise, let's thank the speakers again. And we now have a break. Okay, welcome back, everyone. Are we ready to go? Great. Next we have another recorded talk towards generic type checking implementations in Haskell. And well, I will list all the potential speakers this time. I'm not sure who is recorded. Nikolai, Anastasia, Vladislav, Diana, and Ekaterina.
Hello everyone, my name is Nikolai Kulesov, and together with my collaborators, Anastasia Smirnova, Vladislav Terepkin, Diana Tamilovskaya, Ekaterina Maximova, we're going to present our work in progress on an approach to generic type checking in Haskell. So, type systems are central to programming languages and proof assistants, but are also widely used in all kinds of formal systems. Many different type systems exist, and for each system, usually a few type checking algorithms can be found. Implementations of these algorithms, however, are typically bound to a particular formal system and are not easily available for use, tuning, or modular extension in other systems. While it is usually not difficult to implement a basic type checking algorithm, ensuring that it is correct, efficient, extensible, and user-friendly is not always easy. A generic and modular implementation of type checkers may lower the entry barrier and make different type system ideas more accessible. A language-agnostic type checking library could, in theory, incorporate many of the best practices and make it easier to experiment with the typing rules, get decent error messages, error localization and recovery, and perhaps even get a nice integration with things like language servers to automatically enable features like showing type on hover or providing type context for the current cursor position. We believe that such tooling for prototyping type systems is possible, and in this project we simply start by working with the two well-studied approaches to type checking, which is bidirectional typing and Hindley-Milner's style type inference. The main idea of bidirectional typing is to replace declarative typing judgment with directional judgments for type checking and type synthesis. This makes the flow of information more explicit in the typing rules, revealing what would normally be hidden in the implementation. The usual flavor of bidirectional typing allows for local type synthesis, that is, when synthesizing a type, we only rely on the information about the subterms, not about the outer context. This typically means better error localization, as there is no spooky action at a distance that may cause a typing error. However, this may also mean more user-specified annotations required. That said, there are many flavors of bidirectional typing, and it can even be combined with type variables to enable non-trivial connections between remote parts of the code through unification. A basic implementation of bidirectional type checking, again, is often straightforward. However, there are multiple implementation-specific nuances that impact integration with other components of a formal system down the road. For example, how to properly represent and work with the typing context and how to propagate information properly or efficiently, how to properly cache typing information when computing or modifying the code, and given declarative typing rules, how to determine when to check and when to synthesize types. For the latter question, the answer is given, or an answer is given by the Fanning recipe. The recipe was described by Dunfield and Fanning back in 2004, and then refined and broadened recently in 2021 by Dunfield and Krishnaswamy. The recipe is a way to convert a system of declarative typing rules into a bidirectional type system, and the recipe does not necessarily provide the final truth or the final system, but instead is to be considered as a starting point for an actual practical system, depending on what your rules are. The set of bidirectional rules that are produced by the Fanning recipe has some good properties. For example, it is mode correct, and which roughly means that we definitely can derive a recursive algorithm that would not get stuck on something during type checking. It is also small and annotatable. Moreover, the type annotations that are required by this new bidirectional system are lightweight, meaning they are only in the places where they're really needed, but they're also predictable, meaning that programmers know which parts of the program require annotations. The recipe is outlined again in much detail in 2021 paper by Dunfield and Krishnaswamy, and what we believe is that this recipe is subject to automation in a language agnostic way, and to the best of our knowledge, this has not been done before.
Another well-studied type system is that of Hindley-Milner, which enables synthesis or inference of parametrically polymorphic types for local definitions via lead binding. This algorithm requires first-order unification of type variables and, for efficient lead generalization, a level-based implementation due to Didier-Remy, which is not widely known. Additionally, extending Hindley-Milner with type classes, subtyping, or general constraints further complicates the implementation. Implementing generic Hindley-Milner or bidirectional typing should be relatively straightforward once we have a generic representation for abstract syntax with binders, which is we likely have thanks to FreeFoil. FreeFoil allows to generate an efficient, intrinsically scoped abstract syntax with binders from a given signature that is presented by a Haskell data type with two parameters. The first parameter, named scope, corresponds to subterms with exactly one binder, like body of a lambda abstraction or a lead binding. The second parameter, named term, corresponds to plain subterms, like two subterms of a function application or the first subterm of a lead binding. Type constructor AST is provided by the library and is similar to the fixed point combinator that automatically adds variables and binders in the correct places. The phantom type parameter n is statically tracking the scope of each term. This is a feature of underlying FOIL approach, which is in turn is a type safety mechanism on top of the RPR, which is an efficient implementation of the bound-direct convention for bound variables, which is used by Glasgow Haskell compiler as well as Agda. The library implementation of FreeFoil provides convenient template Haskell helpers that work well with parser generators like BNF converter, making it easy to develop prototypes for small object languages. And importantly for us, FreeFoil comes equipped with efficient generic capture warning substitution and alpha equivalence checks.
Now, by default, FreeFoil works with just one signature, which is a problem when syntax of terms and syntax of types is mutually recursive. For example, types may be used in annotations for lambda expressions, and terms may be used in dependent or refinement types. Now, while the actual current implementation of the library provides more flexibility with that respect, truly mutually recursive definitions like this are not supported at the moment. So when using the FreeFoil for type checking, we have to consider what situation we're in and make a decision. In particular, if we have only simple types, that is, there are no binders that are allowed to bind type variables, then we simply use the FreeFoil on terms and treat types as built-in things that are not of concern to the FreeFoil. However, if we do have binders for type variables, but they are separated, so we have binders in terms that bind variables that have variables for values, and we have binders in types that bind variables for types, then we can just use FreeFoil on the two definitions separately and use it this way. Now, if terms and types mix, then instead of applying FreeFoil, which will not work in this case, we are combining the syntax of both into a unified syntax. Now, this is a shortcoming of the FreeFoil, but first of all, want to point out that hypertypes library which is defined by Yer Chuchim, offers a generalization of data types a la carte approach that supports mutually recursive definitions. However, combining it with the FOIL or any other intrinsic scoping mechanism is maybe an interesting research direction, but it would require significant changes to the user-facing interface. So we stick with the free FOIL for now and just embrace the unified syntax. That said, we think that such unification of terms and types also has a few advantages. In particular, if we unify the syntax, at least at the end of the parser, this simplifies the grammar, usually at least. It makes sure that all of the template Haskell machinery still works well. And because the separation is delayed, the error messages that the user gets are typically better. Instead of unexpected syntax, the user can get a proper context of using say, a type variable where a regular variable or the term level variable was going to be used. And of course, if in the future the object language is supposed to grow and incorporate features such as dependent types or refinement types or features like scope type variables or anything else, then it is very easily done. You do not need to do anything extra. Now, the FOIL distinguishes scopes of terms via phantom type parameter. And one of the main features of the FOIL is zero-cost syncing. It is always safe to coerce a term into a scope that is larger. However, this is of course not true in the other direction, right? When exiting a local scope, we have to check that whatever term, if we want to coerce to a smaller scope, we have to make sure that our term does not have these extra variables, does not make use of them. So in the type system, that means that in a non-dependent setting, for example, when we're inferring the type of the body in a lambda abstraction or a lead binding, we then need to unsync, ensure that the type is non-dependent. And so intrinsic scoping and mixing of terms and types demands this check for us. But also, because we have to perform this check, it contributes to, again, a better error message when we sometimes misuse accidentally type and term variables.
For now, we are testing the waters and getting comfortable with the free FOIL. We have implemented a highly minimal type inference and are working on the efficient level-based generalization before generalizing the entire algorithm. Similarly, for bidirectional typing, we have explored system F with the unified syntax and unsyncing of types, and are now looking for a proper generalized interface. Our project is available on GitHub and is partially documented. In the near future, we plan to generalize our implementations and sketch automation of the Epiphany recipe for bidirectional typing. We also aim to adapt HMX to a language-agnostic variant based on free FOIL. Finally, we would like to implement several test type checkers using our library. This is all. Thanks for tuning in. Now we will be open for questions or comments on our work.
Great questions when we have the speakers online.
Hello again.
Hey, can you hear us again? Looks good?
Yes.
Okay, great. Right. So I have two questions now. Let me actually think of the second one. Right. So with you mentioned that terms and types are use the same namespace in your approach, right? And then you said that also helps with generating better error messages. But yeah, so for some languages where these really are separate namespaces, then you would not be able to to implement those languages. Is that correct?
Do you mean if you allow users to define their own like types and values and mix those namespaces?
Yes, when those two namespaces are truly separate and users can access either one and there's no no shadowing.
Right. I don't think that. So I think that can be handled. What we are talking more about is mixing the syntax of both terms and types, not necessarily the namespaces. By default, of course, the foil will use the same sort of namespace for local variables, but you can still disambiguate them further when they're used as types versus when they're used as terms, I think. Yeah, I don't I understand the question. I don't immediately see sort of a big problem with that, but I also don't have an immediate good solution, I guess.
Okay, good. Other questions? Otherwise, I was able to think of the other one again. At the very beginning, you mentioned that you have multiple use cases for this, also better error messages, and also maybe IDE integration and so on. Which in the end, those parts, especially for maybe the IDE integration, should not even be that dependent on how the type inference is implemented, right? Like
Exactly, yes.
Could be that there's some some general metadata that is completely independent of the inference implementation, and maybe even of the term type. Not sure, but yeah, did you think about separating these two concerns, or is it just very convenient with basing both of them on free foil? Do you see some synergy between that?
Yeah, we have been thinking about this with some other students also. There isn't any progress to report there yet, except that I can say that there is this query-driven architecture for compilers, and in particular in Haskell, I believe there's a library called Rock that sort of dips into that. And so when developing a type checker, it's good to have that architecture in mind already, on the one hand. And the way that you would use that would depend, I think, on a specific, or at least in general, on a class of the type checking algorithms that you're about to use. And that would also depend on so there are two things: the interface to the type checking algorithm, and which is both about the going from the typing rules to the actual algorithms, but also in breaking apart the type checking algorithms into smaller pieces or smaller methods that can be used more incrementally by the language server, so that you do not have to recheck the entire source code every time, for example, right? And also, to be able to do things like show me the type on hover, you don't need to check anything. You just need to store the information already somewhere.
Yes,
So there's a
exactly.
separate question of how you store your ASTs such that this information is readily available and inspectable, how you annotate them with type information, location information, how you mix that. So I guess those are the slightly separate things, but they are still connected to each other. At least I have not fully figured out for myself how you could completely separate those concerns. So our plan is to try and do that for maybe specific algorithms. First, implement them with this free foil approach, just as in non-query driven way, then do the same with the query-driven approach and see how we can properly extract the interfaces such that they are in the most configurable, so that we have the most tunability or configurability out of that. I hope that answers the question.
Yeah, yeah. Query-driven, that sounds very appropriate. Okay, great. I see you have some further thoughts in that direction as well. Do we have other questions? Okay, then let's thank the speakers again.
Thank you. Thank you for listening.
Great. Next, we have MCTT, building a correct by construction proof checker for Martin-Löf type theory by Chunyang Cheng.
Thank you for the introduction. Hello, I'm Junyoung Zhang, as introduced, or Claire Zhang, if you prefer English name. And this work is about the providing a verified proof checker for Martin-Löf type theory. This work is done with the Jason Hu, who is currently in AWS and former doctoral student of Brigitte Pienka, and the Antoine Gaurin and Brigitte Pienka. So I think everyone in this room agrees that the correctness is very important for software. But I'd even say that the correctness is even more and more important as time goes. Starting from the research community, we already all know that concert is there. And there is some industrial formal verification arising. And even the government says that the security and memory safety and correctness, those kind of things becomes important. So how can we say that the verification itself is correct? We use log, agda, lean, agda, but all those have some trusted size of code. Size of trusted code in this is in line number of code, so it depends on the implementation language. But like the concept is, the more important concept is that the soundness bug, they have, each of them has some soundness bug or some other bugs. For example, in case of log, there is 50 soundness bugs since the 2014. And for lean, there are 5. I mean, it is young and the size of trusted code is very small, but there are 5 soundness or seg force bugs because they are implemented in C++. So soundness or seg force bugs since 2020. Maybe the mic position is not so good. I should adjust it a bit. Yeah. And in case of Agda, we have 80 soundness bugs because of, as you can see, the size is very big, and there is no separated corner. So the size is very big, and there are lots of soundness bugs since 2015. So what it needs is verified implementation of a verifier. However, correctness is not the only important factor in terms of verified implementation. We want an implementation, not just a proof. So efficiency is what matters. We want to verify the implementation to be at least usable. We don't want to be like super fast, like blazing fast. We don't need to. But that should be at least usable. And the implementation extraction should be human readable, because extracted implementation should be checked by reader so that the extracted implementation is already implementing the correct one. And maintainers might want to add some task features to the extracted implementation before actually verify it. So we want the human readability of extracted code. And the other one is, one of the important one is extensibility. Because if it's just restricted to a toy language, then why do we want to even implement it? We can just prove some important properties on that toy language, and that's it. So all these factors, including correctness, is very important for the verified implementation. So we introduced the MACTT, correct by construction proof checker, whose focus is on correctness, efficiency, usability, and human readable output for a core MLTT with cumulative universe hierarchy, inductive base type, in our case currently the Peano natural number, and the other future extensions, like there are ongoing works on the future extensions. So let's see the entire structure of MACTT. There is a core part of the MACTT, consists of the front end, which contains the verified parser and elaborator. And what elaborator does is that in our corner, we have syntactic representation of the system, and elaborator elaborates the parsed AST into the syntactic internal AST by using the scope preserving elaboration. This scope preservation is proven in code. And we have semantics to evaluate the AST and read back from the semantics to do the normalization by using those pair. And this normalization, and together with those models about the evaluation and readback, we prove the decidability of self-typing. And because we have the decidability, we can provide the algorithms for the typing and self-typing. And we prove the soundness and completeness of the algorithmic typing and self-typing regarding to the declarative typing and self-typing using the decidability of self-typing. All of this is extracted into OCaml with the OCaml written vector and pretty printer. And this entire structure provides the end-to-end proof checker that programmer can provide the program written in string, and then it checks whether it is very typed or not, and normalize the program given by programmer and returns the normalized result. The entire structure, including OCaml and log, is within the 20,000 lines. And let's see what's the main challenges to build this kind of big structures into log. One is the simple yet efficient semantic domains. We evaluate the AST into semantic domain and read back from that. So normalization is basically depends on the efficiency of the semantic domain. So we want the semantic domain to be very efficient, and we need to prove the decidability of self-typing And to prove that, we need some relations about domain because we have the syntactic relation. We also we have a syntactic translation from syntactic AST into domain. We want to have some kind of models in domain to actually say what kind of terms are related in terms of syntax. And the final thing is the typing rules for cumulative universe. And this requires a careful treatment to make it actually algorithmic. So we will check each of the challenges one by one. First is simple yet efficient semantic domain. The common model of the dependent type theory, or like in general type systems, are preshift model. And there are another model called untyped lambda calculus model. What we usually use in our brain as a functional programmer. And this first model is problematic in the sense that it has lots of categorical structure and it's more complex to execute. You need to preserve all the categorical structure when you prove something about that. So it's hard to prove and hard to extend. On the other hand, untyped lambda calculus model we all know how to execute it. We know, for example, if we want to add some features to functional programming language, then basically what we do is adding some features to untyped lambda calculus. So we know how to extend it. That's why we choose the untyped lambda calculus as our semantic model, semantic domain. And let's go back to this entire structure. I said that we evaluate and read back from the semantic domain, semantic model, domain model. But the evaluation and read back also requires some kind of model because AST, the typing requires subtyping, and subtyping requires equality, convertibility between two types. So we want to have some kind of notion in domain models as well. We also need some kind of equality model in terms of domain as well. So we need some kind of semantic relations, but the problem is that when you want to define the relation between types, we need to define the relation between terms. Why? Because, for example, in this case, we have the pi type. In case of pi type, we first check whether the argument type is related. And if the input is related as a term, we want to say that the return type is also related. But note that there is this pointer that from the definition of type relation to the term relation. The more problematic thing is that in term relation, there is a reference to the definition of type relation. So in this case, when you want to say that two terms f and f prime is related, we first need to say that it is related by some type, some equivalent type. And in the definition, we also need to refer to the input argument type and the return type. So there is an inductive type relation and the recursive term relation that depends on the definition of inductive type relation. This is something called induction recursion, which is very niche feature that's supported by only some proof assistant. I mean, it is like natural in terms of paper proof, but like it is in terms of proof checker, it is not so natural. So in case of log, they don't even have one. So how can you encode induction recursion in code, in ROC, I mean, in ROC? So what he did is actually combining these two into a single predicate, which is the functional type relation that returns term relation. This is possible because only because ROC has an impredicative proof. Because, for example, universe I may return some term relation that itself is universe. if the universe contains like universe 5, then one of the relation in that universe is relation between universe 4s. So we need to handle that kind of recursively defined types into the impredicative universe proof. However, if we start to use functional relation anyway, then why should we stop on the functional relation? Like, why should we say that output ER is unique? All we care about is whether what kind of terms are related by the term relation. So we don't even need to care about the exact ER. So we can use weakly functional relation. By weakly functional, I mean it should be relation. Weakly functional relation because by weakly I mean the output ER is unique only up to relational equivalence. By relational equivalence, I mean the two relations relate the same terms. So if M1 and M2 is related by R, and M1 and M2 is also related by R2, they are like the if and only if, then we don't care whether it returns R or R2. Then why do we care about like changing the notion of functional relation into weakly functional relation? That's because there are some advantage, and the specific advantage we get in this case is we can remove several instances of functional extensionality from our mechanization. It makes the dependency from the mechanization less powerful, and also it makes the proof much easier to carry on, because in case of functional extensionality, we need to apply that kind of functional extensionality on all different kinds of functions. But in this case, with the functional relation, weakly functional relation, we can use general rewriting feature in log. Now, the final challenge is subtyping. And why subtyping matters? I mean, why the cumulative universe is not enough? This is our original mechanization. And our original mechanization has this rule. If the type is where type in the universe, type is where formed in universe I, then that type is also where formed in universe 1 plus I. However, this has a very critical problem in terms of algorithm. Let's see this example. This example is clearly where type because we can apply the cumulativity rule on the variable y. Let's extend it a bit more. We just surround it by the one more function and function application. And it is still well typed in terms of declarative version. But if we change it into the bidirectional version, in algorithmic version, problem appears. In bidirectional type checking, if there is a if there is a function application, we first infer the function part, and the function part returns the this type. Function inference for the function part returns this type. And now we have a problem because this return type of the function part is not same as the type we want to check. And there is no way to connect these two with this rule. So in case of Agda, they use the constraint solver to deal with this kind of issues. But using constraint solver in the mechanized implementation is very complex, and it is like it shows some kind of unbased approach in terms of the type system design. So we avoid this rule, and we use this rule. In case of rogue, they implemented something like this, and their rule is their rule is first, if there is a subtyping relation, we can convert the type from supertype to subtype. And if the universe level is smaller than the bigger universe level is smaller, then it is subtype. And if the argument type is equivalent and the return type is subtype, then the pi type is also subtype. With this rule, still the function part improves the same type, but now this return type has a subtype relation by this rule. And now we can apply this subtyping rule to get the correct type. In general, this kind of problem happens in any negative types, any types that can be only eliminated by applying some observation. So we need to do this kind of covariance subtyping if we want to get a bidirectional type checking for those kinds of negative types. Let's see all the technical challenges are resolved. Let's see the actual implementation of our MACTT. This is the subtyping implementation for normal form types. A and B are both normal form. And it returns whether the A is subtype of B as a normal form, or A is not a subtype of B as a normal form. This is the extracted code from the raw code. And as you can see, the code implementation is very clear in the sense that if there is two types, two universes, then we just compare the universe labels. And if there is two pi types, we compare the input type, whether they are equal or not. And we compare the return type as a subtype relation, using subtype relation. Same for the general subtyping implementation. So if we have the input type A and B, we check whether A is subtype of B or A is not subtype of B. This is done by normalizing A, normalizing B, and checks whether their normal form is actually in subtyping relation. Extracted code is like that, like the same for that. Like it normalizes A, and then normalize B, and then check whether they are in the subtyping as a normal form. Now we can also see the whether it is really usable in terms of the efficiency and like the speed. For that, I'll show you some small example. This NRA is a large elimination example. It returns the type based on the input value, which is only definable in dependent type. And this function is a NRA3 type, so basically ternary function that takes A, B, and C, and just add them up together into a single natural number. And this part is just a weird way to call it. Weird way to call this F321. I use all these recursive things just to make it easier to apply all those things together, but like it's not obvious. Whether it is easy to read is not obvious. So, but basically the code is something like F321. So let's execute this. Where is my mouse? Here. Oh, I should clear. That's also a spoiler. There are many spoilers. Yeah, but yeah, let's see first. Cat. Maybe I should like the yeah. I think I should increase the font size. So let's see. Cat. Example. Let. So here we have the definition of NRA. This is some interface in a sense, interface to make it easier to use, make NRA easier to use. And we have n equals 3, and where is this interference? But n equals 3, and the app is just NRA 3. And this is the actual body of the app. It takes 3 arguments and add them up. So if we execute this, where is the command? Yeah, here. If we execute this by this mactt, then it gives this result. The input expression is well typed, and the normalization result is 6. I mean, we add 3 to 1, so it should give 6. And as you can see, if we ignore that percentage thing, which is about the OCaml compiler set, it's basically done like within a split second. So there is no problem in terms of usability, at least for this kind of small example. Our previous implementation was in Agda, and I don't want to say too bad things about Agda, but in their case, our previous implementation, we didn't use too much proof irrelevance. So in the implementation, something like this takes 5 seconds to actually finish the execution. So that one is definitely not usable, but this one is much more usable compared to like any toy examples or anything. So let's go back to the presentation. Now conclusion is, first, McTeacher's contribution. We have the first end-to-end verified proof checker with cumulativity and inductive base type. And it gives us, it verifies the efficient normalization of cumulative type theory. And we recognize that the weakly functional model allows us to avoid functional extensionality in almost all cases, except just one case. There is some one not so necessary case, but it's too hard to avoid by hard I mean it requires too much code, so it's too hard to avoid the functional extensionality. So we just use functional extensionality just for that one case, but it is not essential. So basically, we can avoid functional extensionality in almost like basically all cases. And we also noticed that the simple universal cumulativity does not work well with negative types. So negative types and constraint-free bidirectional type checking. So we realized that the covariance subtyping should be there, at least for all the negative types. Our future work is, first we'll add the propositional equality types and user-defined inductive types, and modal types from Cocon allows us which will allows us to do verified metaprogramming within the MRTT. And the last, more practical future work is adding attaching this verified kernel to real proof of systems such as Cork, Lean, Rock. It should be Rock, Rock or Lean or any kind of language with kernel. I cannot add Agda here because Agda doesn't have the real kernel. But yeah, any kind of proof of system with kernel, so that so that we can actually check their fragment of their proof as by a verified proof checker, so that we can give more guarantees about verification. This is my talk about McTT, and if you have any questions, please ask. Thank you for listening.
Hi, I'm Fafonia from Minnesota. So I have a question about the subtyping rule of the pi types. It seems that you are not allowing the domain type to have the subtyping relation. Is that intentional?
Contravariant subtyping is intentional in the sense that we have some idea, and I think it works, but it was not so clear. And in case of log, they don't have the subtyping for contravariant subtyping for argument. So we first implemented something that is well known first, and then we will extend it to the contravariant subtyping as well.
Hi,
Hello.
thank you for the very nice talk. So you mentioned that these subtyping rules, you expect to add them for each negative type. So if you had like sigma types, I would expect to see another rule like the pi type?
Yeah, I think there should be two different rules for, not two different, but the two different subtyping derivation for the sigma type.
Gotcha, thank you.
So you mentioned that your inductive recursive type is not, like, induction recursion isn't supported in Coq, and so you found a way around it in this situation. But then you also said, like, you wanted to extend this to user-defined inductive types, and it sounds to me like you're trying to build a model of Coq inside Coq. What is your idea for how to sort of square that?
One of the difference of this one and Coq is that this one is set up yet. I mean, I'm not sure when we will add that, but the key difference that allows us to do this almost no axiom. I mean, there are some axioms, but almost no axioms in Coq is that we don't have proof. We don't have impredicative universe in our mechanization. So using the power of impredicativity, we can have the proof power difference between the meta theory and the object theory. So that allows us to actually mechanize object theory within the meta theory, like to the normalization and decidability of conversion.
Also, can you say what is exactly the type of this function that you are defining?
This one is basically just the relation between two domain terms, and this one is take two domains as a type, and also take this ER as another argument, and it relates those three as a functional relation. So first two is somewhat like an input, and this ER, or the type of ER, the relation between two domain terms, is the output of the proposition. So it's the real type of the inverse. The type relation is that first the level, natural number to domain term to domain type to domain type to relation of domain term to proposition. Yeah.
Hey.
Yeah.
I was wondering, is efficiency the only reason you switched from Agda to Rock?
If there are two reasons. Basically, the efficiency is one reason, and the other reason is that let me go back to the actual slide with the reasoning. So the one of the reason is human readability. So the output of Agda has lots of coercion that based on the unsafe coercion in Haskell. So the code is very hard to read because unsafe coercion is not very common thing as a high-level programmer to use in Haskell code. On the other hand, the cost extraction, if we provide proper separation between proof and the settings, it gives us a very good human readable output, so that we can actually, as you can see in this slide, even though there are some less natural matches, it is very what human would write. Yeah.
Did you consider trying to putting the proofs in SPROP, or is the support? Did you consider trying to put the proofs in SPROP? In Agda?
We didn't, but I'm not sure whether that is very extensible. That's basically the problem. If we have to add some more features, I mean, we don't even know whether we will add some more powerful features like homotopy type theory or something like that. I mean, we probably not yet, but if we want to add some more features, then it's better to have less restriction in terms of encoding type. So yeah.
I'm not sure if I.
We didn't consider whether we didn't consider sprobe as a good candidate for the our encoding. Yeah.
Okay, thanks.
Can you go to your figure that just kind of laid out all of your results?
Right. Resource. Okay. Here.
No. The picture with
the structure. You mean?
Yeah.
Here?
Yeah, this one.
This one.
And you said that your total proof was about 20,000 lines of
Yeah.
rock code. Do you know how that breaks down among the various results here? Like, is it mostly in talking about decidability of subtyping, or how much is in a connection between the syntactic and the algorithmic?
This part.
Okay.
It's mostly about the decidability of subtyping. This part takes 13,000, if I remember correctly, and all other parts, including OCaml things, contains about 7,000. So like it's mostly about the semantic and decidability of decidability of subtyping. Yeah.
So I'm curious about the selection of type theory features.
Mm-hmm.
Some might say cumulativity is a complexity best avoided. Or did you specifically seek out that challenge? How did you select that?
Cumulativity, we choose cumulativity because cumulativity's model is, we thought that the cumulativity's model is the most natural in terms of the universe hierarchy. And it also gives us enough challenge in terms of the power model and growing model. And it hasn't been, as far as I know, other than our own other works, it hasn't been mechanized in any other proposition. We have Agda mechanization in other paper, but other than that, there is no other mechanization for the cumulative universe, for hierarchy of cumulative universe. So that's basically why we choose the cumulative universe, because there is to repeat myself, first, there is we thought that it is very natural in terms of domain model and power model. And second, there is some enough challenge. And third, it hasn't been very well explored except our own work. Those three are the reason we chose the cumulative universe.
Nice. And smaller questions, maybe. I hope I didn't miss that. How do you represent recursion in the end?
Sorry?
How do you represent recursion? Do you have, is that a primitive syntax or?
Yeah, it's primitive syntax. As you can see in this example, we use this black.
Yeah,
and
so
that's
pretty much the kernel representation as well?
Yeah, it's
okay.
like just
sense.
the recursive eliminator of natural number. Yeah.
Okay, great. Great, let's thank the speaker again. And next we have a live remote talk by Andras Kovacs about eta conversion for the unit type is still not that simple.
What's that? Give me a second. Oh, okay. Cool, cool. Chris, should I not move him in? Sorry? Should I not move him in?
Hi, everyone. This is the AV guy. It sounds like there's been a slight delay, so we're going to, I guess, just take a quick break for a couple minutes.
Any further questions, maybe for the previous speaker? Or do you want to? Yeah.
If you have any more questions, I can take some time.
Great.
Yeah, sure. I mean, I can just.
So, very important scientific question. How did you choose the name and MICTT?
Wow, that's a hard question. So, you can choose either mechanized type theory or McGill's type theory. Choose one.
Very good.
Hello, Andres. Can you hear us?
Yes, I can hear you fine.
Okay. Feel free to share your screen whenever you're ready, or share your slides whenever you're ready.
Okay. Okay. Yes, I can hear you.
Perfect. We're all set. Thank you.
Okay. I'm András Kovács from University of Gothenburg and Chalmers University of Technology. And hello, everyone. I would like to talk about eta conversion for the unit type, which is still not that simple even after this talk. So, what is the problem? You can see here this rule for the unit type, which really just says that if you have two terms of the type, then they are convertible. And there are no other conditions. You can just take any term whatsoever and any other term, and they will be convertible. And then one issue with this is that, so because they really can be any terms, they can also be distinct bound variables. And another problem is that if we also have eta rules for pi types or sigma types, then we automatically get many more types which are definitionally uniquely inhabited. For example, you can take any function type which iterators in unit, and it's also going to be definitionally irrelevant because every inhabitant is just equal to some lambda, some constant lambda returning the element of the unit type. And you can also take products of irrelevant types, and they are also going to be definitionally irrelevant. So this means that conversion checking has to compute some types. And but there's one question: is if this is so complicated, then why do we even want to have unit eta? And I would say that in many situations, unit eta is not essential, but it is nice to have. And another thing is that if you have a good implementation for unit eta, then it can be reused more generally for other features, which also imply some definitional irrelevance. For example, singleton types, extension types in cubical type theories, and also the implementation of strict propositions. So what about unit eta in current implementations? In ROC and Idris 2, there is really no attempt at supporting it. There's just a purely syntax-directed conversion, and that's it. In Lean 4, so the story about Lean 4, I looked at it 2 days ago. So if you just write down this this definition of an eta rule for the unit type, it works fine. But if you write down a slightly different eta rule for the functions going from unit to unit, then this is rejected. Yeah, so this is rejected, and this is a known issue. But you can see that it's not a fully robust implementation. And then the actual kernel implementation of this is also not so nice because it works by calling an infer function on terms, to get their types and check if the types are unit. So the conversion checking is trying different strategies to convert terms. And if all of these strategies fail, then in the very end, we are calling essentially an infer function to recompute the types of the sides and then check if they are unit. And of course, this is not very efficient because this infer function is doing an arbitrary computation on these terms to kind of pull out the types from them. And in Ogda, we have type-directed conversion, which is pretty good in terms of completeness of conversion checking, but not quite complete. And it is also fairly inefficient because it always computes types, even if they don't really make a difference. So in this talk, I will talk about a very simple setup at first, which is just bidirectional elaboration without any meta variables. And I have lots of code examples, and we will see how many of those I can actually explain. And in the second part of the talk, I will briefly talk about what happens if we add meta variables in the mix. And as usual, it's not going to be simple, so I just give a brief overview and no coding examples. And this whole thing is partially implemented, but I haven't yet benchmarked. And so this is not really the final word on anything. It's more like just my experience looking at different designs and just seeing which one feels nice and which one feels kind of sensible. Okay, so the very basic setup comes from Thierry Cocon from 1996, an algorithm for type checking dependent types, which is essentially making a distinction of terms and runtime values. And this can be understood as an interleaving of elaboration and normalization by evaluation. And I strongly believe that this is a very nice nice approach to elaboration in general. And it also has excellent performance and also very good ergonomics in terms of the implementation. So on the left, you can see a definition of terms, which is this small inductive type for some type theory, which has variables, pi types, lambdas, applications, U for universe, and then the unit time. And on the right-hand side, you can see neutral values, which are just variables or applications of neutrals to values. And then values themselves have a very similar structure to terms, except that there is an explicit embedding of neutrals into values on one hand, and on the other hand, all the binders are replaced by actual closures or actual functions in the meta theory. And then this will enable us to do beta reductions in a nice and efficient way by just reusing the function applications from the meta language. Okay, and so what is the extension that we want to make? So we add lazy types as an annotation. So I'm using this lazy here in kind of an informal way. So I'm just assume that this is some kind of strict functional language, some kind of pseudocode for a strict language, and I'm explicitly annotating what I want to be lazy. So I put this lazy type annotation on neutrals, and this is really just the type of the neutral. And then, so how do I compute? Okay, so let's continue a bit more with the explanation of this setup. So what are the functions that I need? I need an evaluation function, which evaluates terms into values. I need a conversion checking function, which compares two values in a recursive fashion and then throws some exception if they are not actually convertible. And then I also have the two directions of bidirectional elaboration. Inference returns some term alongside with its type, and then checking takes a type as an argument and returns a term. And then let's look at, so what happens in evaluation if I have these type annotations on neutral values? So this up function, as you can see, which goes from values to values to values, is kind of the semantic implementation of application. And so if on the left-hand side you have a neutral value, then we create a new neutral value on the right-hand side. And we also compute using this type of up function, the type of this application. And it's not very surprising what it is doing. It just picks out kind of the binding from a pi type and just applies it to a value. So this is just an instantiation of the codomain type of a pi. And it's important that we do this computation lazily. So this is just a thunk, and we don't really compute anything until we actually look at this type. And then you can see that in evaluation, if I have an application on the left-hand side, I just call the semantic equivalent, like the semantic correspondent of application on these evaluated terms. Okay, and then to finish up this version, I have conversion checking, and I have a function which tells me if some type is irrelevant. And irrelevant in the sense that all inhabitants of the type are definitionally equal. The type is irrelevant if it's a unit type, or it's irrelevant if it's a pi type, and then when I instantiate the codomain with a fresh variable, it is also irrelevant. And any other type is not irrelevant. So in conversion checking, now I can look at the case when I have two neutral values. And so what I do is that I try to convert the neutral values on the two sides. And if that doesn't work because I get some exception, then I can test the irrelevance of the type. And in this case, because I'm assuming basically homogeneously typed conversion checking, I can just randomly choose to look at the type of the left-hand side or the type of the right-hand side, because just by assumption, they are definitionally equal. So how does this work, and why is it maybe not so bad? So one thing which I like is that conversion is still syntax directed, and essentially the whole look and feel of conversion and elaboration is still very much syntax directed. And really the only place where we have to even care about types is just evaluation of applications, and then in conversion checking this single case when we are looking at the neutral values. And because of the laziness, this means that types are only computed if conversion checking depends on unit eta. So we usually, by default, we assume that things are actually definitionally relevant. And if we get into if we throw some error, but then later we learn that this is not actually an error because of some irrelevance of some neutral, then types are computed, but otherwise types are not computed. So if you have some program which doesn't actually rely on the unit eta, then types are never going to be computed. But in the case that types are computed, then they are computed reasonably efficiently. So, and let's look at an enhancement of this setup. And this is kind of a pretty obvious optimization on the previous version, because if you think about it, the elaborator, so the bidirectional elaborator, already computes many types, because part of type checking is to do conversion checking on some expected types and some inferred types. So whenever that happens, because types are computed anyway, we can also compute relevances of types at the same time. But let's start from the beginning, and let's look at what kind of modifications we need to make on the previously seen functions. So first, for values, we add another annotation. Now this is a maybe bool annotation. And this means that, so just true means that the type is irrelevant, just false means that it's relevant, and nothing is that we don't get any extra info, because this maybe bool is some extra info which we really only get from the elaborator, and we don't get it from evaluation or from anywhere else. And then what about the implementation of application? So if we have a neutral case, so if we have a neutral value on the left-hand side, then we need to update the irrelevance of the output. And the rule here is simply that if we know that something is irrelevant, then like if we have an irrelevant function type, then applying it to anything is still going to be irrelevant. And in general, in Martin-Lev type theory, if you have an irrelevant thing, then you can never extract by computation an irrelevant thing from it. So all the eliminators of the irrelevant types can only return irrelevant values as well. And in every other situation, we just don't know anything about this extra annotation, so we just put there some nothing. And then we have this conf type function, which is a specialization of conversion just for types. And what it does is that it doesn't return some unit, and with some possibility of exceptions, it returns a maybe bool, exactly the same kind of maybe bool that we've seen before. And you can see here that I do the usual structural recursion on values, but in each case, I just return as a return value this computed relevance. And this is basically no extra overhead on the top of ordinary conversion checking for types. And I also extend terms with an extra constructor for annotations, like these relevance annotations. So the general idea is that in type checking, I do some conversion checking, I learn some relevance, and if I do learn something about the relevances, I just put it into terms. And then when I evaluate those terms, I can plug in these irrelevances in the neutral values that I get from evaluation. And kind of the final piece in this is conversion checking of neutral terms. And now I have some extra information about irrelevances of the two sides. And you can see here that first I can just test if I know that that these neutrals are irrelevant from the information that I get from elaboration. In that case, I do not have to compute anything. I immediately know that the sides are convertible. And otherwise, I do a conversion checking of these neutrals. And if the conversion checking fails, potentially I still have to compute the relevance of the type. But that relevance computation can be also potentially shortcut by the same information that I get from elaboration. So this is kind of the general scheme. And then this can be enhanced a bit more, but I think that these enhancements are potentially too clever and too fancy. So one enhancement is that we might also want to memorize the relevances computed during conversion. So we have seen previously, like for example, this is irrelevant is a function that we call on types, and potentially we also want to memorize all the results of these is irrelevant function calls. So this is one potential optimization, and for various reasons, it would be a bit annoying to actually implement in an elaborator, but it's perfectly doable. Another optimization is that we don't just return a nothing from conf tie if, for example, we hit some neutral type, but we could return some representation of a blocked computation of a relevance. And then one example for this, so let's imagine that you have a potentially very big record type where all the fields are irrelevant, except that there is just one field which has a neutral type. And if we go back a little bit, so we do this conf tie. So if we are doing a conversion checking on such a big record type, conversion checking, like testing it against itself, then we would get nothing as an output of like nothing as an information about the relevance of the type, because it has just one field which is neutral. But then this partial information, like this partial computation that we do when we compute these relevances, could be also represented in some way and could be also returned from this conversion checking. But anyway, so all of these fancy enhancements should be benchmarked, because it could be the case that they are pointless in practice. And let's talk just shortly about what happens if we add meta variables into the mix. There are many complications, and most of the Agda issues relating to unit theta are really about the interaction of meta variables and unification and unit theta. So essentially, this is where the incompleteness of Agda comes from. And but probably I want to skip this Agda example and just talk about what has to be done if we want to have unit theta together with unification. So the first task is to detect irrelevant unification contexts. What do we mean by this? So let's assume some bound variables f and g, and then let's look at this unification problem of fg alpha being unified with fgt. And but now the situation depends on the types of f and g, because either f's or g's return type is irrelevant. In that case, we cannot uniquely solve this alpha meta variable to t, because the whole problem could be just replaced by just one invocation of the irrelevance of some type. So if we do produce a solution of alpha to t, then that would not be a unique solution, because in some other part of our program, we could potentially solve alpha to a different solution. So what we need to do is that during unification, if any enclosing neutral has an irrelevant type, then if we have any error, like if we have any rigid mismatch of values, or if we if we have any failure of conversion in such a context, then we just have to bubble up to the innermost neutral with an irrelevant type and just convert the failure into a success, because actually the error occurred in an irrelevant context. And then similarly, we cannot really solve meta variables in such irrelevant contexts because they would not be unique solutions. So then attempting to solve a meta variables in irrelevant context, again, should throw some exception, which then bubbles up and then gets caught at the irrelevant neutral. And then the second thing is to detect the contractible context in meta solution candidates. So again, let's assume some bound variables f and g, and I want to solve this alpha equals fg alpha. And normally, without the unit theta, this would be an occurs error. So this is the infamous infinite type error that we often get from GHC. But if we have unit theta, it is not necessarily an error, because if this alpha occurs in a contractible subterm, we can just replace that subterm with the inhabitant of the contractible type. And by contractible, I mean that some type has a unique inhabitant up to definitional equality. And you can see, for example, that this might be a solution for this unification problem. So again, really the task is to, like when we do this right-hand side processing in the meta variable solution, we have to catch errors, and we have to throw some errors, but then catch them contractible enclosing neutrals. And then the third task is, again, to detect irrelevance, but now in a higher order pattern checking situation. So you can see this equation for alpha xx equals x. And then normally this has two solutions. And there is no reason to pick one solution or the other. So in Agda, and I think also in Kok and Lean, there would be some kind of error or some kind of warning or some kind of postponement of this unification problem altogether until we learn more information. But if the type of x is irrelevant, then the two solutions are definitionally equal. So we can just arbitrarily pick one of them, and we have a successful solution. So to summarize, my proposal is to compute types only on demand, but efficiently. And for this, it's kind of an important basic setup that we use Cocon's algorithm and like the basic setup of interleaving normalization by evaluation with elaboration. And the second thing is to kind of piggyback the relevance computation on conversion checking in elaboration, which is a cost that is being paid regardless of what we do with unit eta. So we can just exploit that computation that already happens. And then finally, systematically catching errors and converting them to successes based on the relevance of computational context. And thank you. Maybe we have time for some questions.
So in your conversion algorithm, when you have something that potentially has an irrelevant type, first you check whether they're convertible, and then you look to see if the type is irrelevant. But maybe there's some situations where it's quick to find out the type and long to tell whether something is convertible, and it might be faster to do it the other way around.
Yes, so that indeed might be the case. And but if we are talking, so the point is that we have some freedom how to structure this conversion of neutrals. And if we only have unit eta, then I believe that in practice, like depending on unit eta is not so common. So in this situation, it's probably a good idea to only look at types if we fail, because depending on unit eta is not very common. But for example, if we are depending on strict propositions, then we also have definition irrelevance. And in that situation, it might be more beneficial to first look at the relevance of some type and then try to do the convergent checking, because we might expect that we depend on strict propositions more heavily. But this is very heuristic, so I cannot say like very concrete things about which one is better. But the point is that if we have this setup, and if we also have the extra information coming from the elaborator, then we have choices how to do this.
Okay, let's see if I remember that correctly. I believe you extended the core term type with the new irrelevance information. Is that correct?
Yes,
okay.
I did it.
Yeah. Yeah. So when I see an extension like that, I'm thinking, oh, could that maybe negatively affect the memory overhead of the entire system, because this is the one type that in the end makes out most of the memory, right? Do you think that's a concern, or how often will we create that?
I really do not think that this is a concern. So adding basically, if I wrap a lot of subterms in a single like relevance constructor which only has a bool annotation, that's very, very tame compared to what happens if you look at like what happens if you serialize modules in Agda or Coq or pretty much in any other proof assistant. So it's I think it's fine.
Yeah. Okay. Other questions? Oh, we are already on time. So let's thank the speaker again. And now it is time for lunch, after which we will have our first Okay. Are we ready for the next talk? Is a live remote talk. Yes, that's correct. Semantic analysis of normalization for directional logic programming. And the speaker is Ariadne Sue.
Uh-huh. Sorry, I think I've been somehow leaving the live session. Can you hear me now? Hello?
Yes, we can hear you. I'm just gonna pull your video up real quick. And can you go ahead and start sharing your screen?
Let me share my screen as well.
Perfect.
Great. Can you see my slides and hear me?
Yes, yes, looks good. Thank you.
Great, great. I think there's probably a bit of a lag there, but great. Can I start?
Yeah, please feel free.
Thank you. So this is joint work with Vikram Chaudhary and Neil Krishnaswamy. And in this talk, I'm going to try to convince you that type checking is really proof reductions in classical linear logic. So you might be thinking that you've implemented type checkers before, but don't remember thinking about linear logic. So the aim of my talk is to try and tell you that you really should be. And if time permits, I'll tell you a bit about the benefits of this perspective. So let's get started. We have a typing judgment, and we can see them as predicates, which takes 3 arguments, so context, term, and type. And how do we define such a predicate? Well, we have typing rules. So we can read these typing rules bottom up. So this says, to derive the predicate, which says lambda abstraction has type A arrow B, we're going to derive the predicate, which says E has type B in the extended context. So the colon dash I'm using here comes from the syntax of Prolog. And you also have function application. So the 2 predicates here correspond to the 2 premises on the left. So this is why we can see type systems as logic programs. And now in order to do any type checking, we can simply write a query as a logic program. So this says, well, is it true that E has type A? And hope that our logic program will tell us true or false. So is our problem just solved? We can just do type checking by running a query. Unfortunately not. So let's think about subtyping for a sec. This says to derive that E has type B, we're gonna derive E has type A, or some A. We don't know what it is. We're gonna have to guess it. And then say A is a subtype of B. So in order to resolve this goal, what would happen is we're going to match this predicate E has type A again and see actually, well, it matches with the same case again. And that's why it would go into an infinite loop. So this is why queries may never terminate. So we can't just expect to successfully do type checking this way. So the reason for this is the set of typing rules we could write is too unrestricted. And one way to put more restrictions is called bidirectional typing, which Nicola, I think, has kindly mentioned earlier before noon. So let's have a review of what this is. So Given a normal typing system, we can transform it into a bidirectional one by now instead using two kinds of judgments, so two directions. And first one says we're going to check that E has type A, and second one says we're going to infer that E has type A. So we can, again, write our typing rules using our new judgments. So we're going to check lambda abstractions while inferring function applications. So the choice of whether to check or infer might seem arbitrary at first glance, but these are carefully crafted according to a series of criteria and recipes people have come up with over the years. So this example I'm using here comes from the Fanning recipe. If you're interested, you can read more about bidirectional typing in the recent survey paper by Jana Dunfield and Neil Krishnaswamy. The most important criteria in crafting bidirectional type systems is called mode correctness. What does this mean? Well, the main difference from a normal type system is that now the judgments sort of have a direction to them. So instead of a relation, now there are partial functions. So check takes 3 arguments, so actually 3 inputs, context, term, and type, while infer takes context and term as input, and then give you a type as an output. So this is what I mean by mode, whether something is an input or an output. And saying the bidirectional type system is mode correct basically means that information flows nicely from inputs to outputs, and you sort of don't have to guess anything on the way. Let's actually have a look at an example. So this is a rule for function application. And to check that this rule is mode correct, we're going to start, our starting information would be the inputs to the conclusion. So think of this again as running bottom up, and this is like your goal. So that's your starting information. And so if we know that gamma E1, E2, then we know the gamma in the left premise, and similarly E1. And by similar reasoning, we have gamma and E2 on the right premise. And now looking at the left premise, all the inputs are fulfilled. So by induction, we should be able to get the output of this premise, which would be A arrow B. And then we can grab this output and feed it in as an input to the right premise. So now all the premises are resolved. We can output B as the whole output of the system. And this is why this rule is mode correct. Let's think about if we've designed this rule differently. Say, for example, if we check all premises, what would happen? So again, our starting information would be the inputs to the conclusion. And then again, we have gamma and E1 and gamma and E2. Now this A sort of appears out of thin air. We don't know where it comes from. And this is why this rule is not mode correct. And the significance of mode correctness is really that you can see a bidirectional type system as a type checker if you read it bottom up and it tells you what you're going to do at each step, what are the other goals. And if a rule is not mode correct, you have to guess a type A, which is not ideal. So returning to our previous picture, so this is a bidirectional type system, and we can write the new judgments as predicates, so check and infer, and again writing our typing rules as logic programs. So as we've said before, we've annotated the modes here because it's very essential that all the rules are mode correct in order to read bidirectional type system as a type checker. So this is why we can see type checkers as moded logic programs. And returning to our subtyping example, now we can see it doesn't loop anymore because we've switched from check to infer. And people have come up with all sorts of extensions of bidirectional type systems over the years, and I'm just going to mention one here. So this is called strict bidirectional type checking by Adam Chapala and collaborators. And they're motivated by the fact that previously I could only check lambda abstractions. But actually sometimes we can infer them in order to reduce the annotation burden. So this expression here, suppose we know that increment has type int to int, we should be able to infer the type of this expression. So let's have a look at how to do that. So this would be in the extended context, increment x has some type. But we don't know what this question mark is. So let's go just one more step up. Great. So now looking at the right premise, we can sort of deduce from this that actually this question mark should be an int. And now we can propagate this information downwards and say, well, let's fill in this question mark is int, and then we can infer the type of lambda x inc x. So the thing to notice here is that this int is really an output of the system. So previously I said no matter we're checking or inferring, context is always an input. So here is a case where you have an output embedded in an input. And actually in practice, you also have it the other way around. So input embedding in outputs, or like lots of layers of such things. And actually in Scala, so due to Martin Odusky and collaborators, they color the type. So you can see whether each part of the type is an input or an output. As you can imagine, checking mode correctness becomes incredibly difficult in this setting, because our intuition about how information flows from inputs to outputs breaks down when we have, loads of layers of inputs and outputs. So we really need a better foundation for talking about fine-grained mode systems. So let's have a think about how we might come up with the foundation ourselves. So let's take a simple example. A type which takes list of A as an input and output a B. And suppose this A is an output. So this is really just saying we're going to input a list of placeholders, which is going to be filled in with values later on. And this looks quite messy, so maybe let's treat input as default and label all the outputs. So we're just going to use some symbol to label the outputs, okay? And now instead of saying that this negation symbol labels the outputs, we can generalize this a little bit and say that this negation symbol switches the input-output notion of a type. And that doesn't just restrict to atomic types. You could also switch the input-output notion of like multiple layers embedded type. And what do we want from this operation? Well, we want to say if we switch the input and output notion once, and then again, we should get the same thing. So there's really a sort of classical logic flavor here. And in addition, we want to say that we want some sort of computational interpretation to it, which we know pure classical logic is not great for. And that leads us naturally to classical linear logic, which happens to be a great setting to talk about such things. So let's look at a few inference rules. I'm using the sequence calculus presentation here. So we can think of the left-hand side as input and right-hand side as output. So this rule just says, well, if I get an A as input, I can just send it along and out as output. Second rule says, if we can output an A, well, we can input an A dual. Again, remember, A dual means switching the input-output notion of A. And we can also flip this the other way around. Here comes the important rule, which is called cut. So this says if we can output an A and output an A dual, we can essentially make these two types communicate with each other. So like link them together in the sense that we are going to match with all the inputs in A with all the outputs in A dual and vice versa, so that they sort of don't affect the environment anymore and they can go away. And there are also other typing rules for like and or, and their duals, which we'll omit for now. So to talk about computations, people have come up with all sorts of term calculus for classical linear logic over the years. And I'm just going to use one here. So if we label A and A dual with terms, and we're going to record the fact that we're making T and T prime communicate and link them together. So this is really just sort of tell you how the information flows. And then a program just becomes a collection of such linkings. And again, just linking all the information together. And to do any sort of computation, what we need to do is actually make the information flow. Like this is a dynamic thing now. And that means maybe there are loads of linkings and I'm going to reduce them to like less linkings, or maybe a big linking could be separated into smaller ones. So computation actually corresponds to cut reductions in classical linear logic. So the language I'm using here is due to Uday Reddy in a paper called The Type Foundation for Directional Logic Programming. Notice the mention of logic programming here. And this is especially inspired by Samson Abramsky's computational interpretations of linear logic. And as you've probably seen in other sessions, session types is another great setting to talk about such embedded mode information. And we've chose Reddy's language because it has a natural link to logic programming. So let's have a think about, actually let's look at an example of how we might write such a logic program. So a simple example, write a predicate called not, takes a Boolean as an input, output a Boolean. So the tensor product here is just the classical linear logic version of the AND type. We're gonna say, well, to derive that not A is B, we're gonna match A with a case pattern. If it's true, then B is false. And if it is false, then B is true. So again, remember that this link links opposite types together. So here it's really saying like if A has opposite type to T dual. T stands for true. So to run a query, we can say, okay, we're gonna input a true. What's the output? We're gonna use a variable here and hoping the program will tell us what it is. So this query would trigger a substitution into A and B. Okay, giving this. And now it's gonna match with the first case pattern and say, okay, so this would be the output of our system, and saying X should have the opposite type of false. Again, opposite means switching input-output. And now, as we've seen before, these linkings come from the cut rule. So each step is really a proof, it's like a proof in classical linear logic. And these reductions are proof reductions in classical linear logic. Great. Let's return to our big picture again. So bidirectional type systems, again, we can write these judgments as predicates, check and infer, using constructs from classical linear logic. And now, if these directional logic programs type check, remember we've combined mode with type. So type checking really says that, well, information flows nicely and that everything is mode correct. So therefore, the bidirectional type system would actually be an actual type checker. So this is why we can see type checkers as directional logic programs. And now to run such type checker or doing type checking, we're just going to run a query. And as we've seen before, that this would trigger a series of proof reductions in classical linear logic. Great. So what have we talked about so far? Oh, one more thing missing here. So here we can see that context should be a type in directional logic programming language, which Redis language doesn't currently have. So we need inductive types. And let's recall the syntax, the grammar for context. And so to incorporate the previous example of lambda x dot inc x, the Adam Chapala example, we are going to extend the grammar of context with this, saying this type could also be an output. And this context could actually be written as an inductive type using constructors from classical linear logic. So we've extended a Redis-like language with inductive types and co-inductive types because of the duality, and show that the semantics is what we want categorically. So now returning to the big picture, what have we talked about so far? Well, we've seen that type systems can be seen as logic programs. And type checkers, well, type checkers coming from bidirectional type systems, can be seen as directional logic programs. And actually doing type checking, running the type checkers, correspond to query evaluation, which turns out to be proof reductions in classical linear logic. So that completes the big picture of the talk. But you might be wondering, okay, fine. So type checking is proof reductions in classical linear logic. So what? Well, let's think about how you might write a type checker. So you're gonna write some typing rules on paper and check that they're mode correct, okay? And if they are mode correct, you can read these rules bottom up and get an implementation out straight away. Great. But suppose fine-grained modes are involved, which happens a lot in practice, then we're stuck. We essentially don't know how to do check mode correctness anymore. Our intuition breaks down about how information flows. So what we're going to do instead is, after writing the typing rules, we're going to write them as directional logic programs. So notice that this step here is really not much of a jump. It's really writing the same thing in a different syntax. And if these things type check as directional logic programs, again, because they combine mode with type. And recall the linking thing is like linking, you can only link opposite types. And if everything type checks, it means like every input is matched to an output. You can't make up something out of nowhere. Then the original type system would be mode correct. So we can see our work as using directional logic programming as a formal foundation for mode correctness, which is especially useful in the situations where our intuition breaks down. And secondly, well, by writing now one type checker for directional logic programming language, from then on, we can just write some typing rules on paper. If they type checks, great. Get implementation out of it straight away because they're mode correct. So we get implementations of lots of type checking algorithms for free. So this is why we think it might be helpful to think of type checking as proof reductions in classical linear logic. So that's the end of the talk. Thank you very much, and I will take some questions. Thanks. We're still here. Hopefully.
Questions?
Oh, sorry, I don't think I can hear you.
Oh, thanks. That was a very nice talk, and I like the connection to linear logic. I'm just wondering if this would work if you wanted to do type inference besides type checking.
Yes, yes. So great question. Thank you very much. So as we've seen, okay. So because in logic programming, you can essentially replace an argument with a variable, and then when you run it, it's going to give you like what this variable is. So in the not example we've seen. So if we want to do type inference now, we're just going to replace the variable for type with an x, and it will reduce to a normal form which says what x is.
Thank you.
If that's clear. Thank you.
I think in your abstract you also outlined unsolved problems or further steps that you want to research. Is that correct? Could you
Yes.
elaborate on that?
Thank you for the question. Yeah, of course. Yeah, and thank you for checking out our abstract. We wrote some, so we were looking into how to, essentially we were trying to figure out what Uday Reddy's reductions are, and we were working on a polycategorical framework for it, which we were looking at like Highland-Truman envelope and how normalization actually corresponds to this polycategorical version of normalization, of Unay dilemma. But our future work is first, we've extended with inductive type, and the next thing to look at is binders. So suppose our original type system is system F or something more complicated. And to translate them into directional logic programs, we do need some way to talk about these binders, and we're planning to look more into abstract syntax and variable binding by Marcelo and collaborators, which would allow us to accommodate more expressive type systems in this framework.
Great. Okay, let's thank the speaker again.
Thank you very much.
And our next speaker is Thomas Porter about incremental bidirectional typing via order maintenance.
There we go. Yeah, I think it's on.
Perfect. And then if you don't mind actually taking off the...
Oh, how about this?
Oh, that might work.
Cool. Okay. Hi, I'm Thomas Porter, and I'm going to talk about incremental bidirectional typing via order maintenance. I'm at the Future of Programming Lab at the University of Michigan, and this is joint work with collaborators at the University of Utah. Okay, so first of all, this is very much a work in progress, and I'm as interested in hearing the advice of the experts in this room as I am in talking about my plan. So yeah, very much this is conveying a plan. And roughly in terms of how far we are, I made up these numbers, but we're most of the way through conceptualizing the plan, a chunk of the way into formalizing it in paper and in AGDA. A little bit of implementation work started, and we don't have anything to evaluate yet. Okay, but with that out of the way, our main goal is live programming. That's programming with continuous feedback of some kind. And people have talked a lot about what exactly this is, why it's desirable, how to achieve it. But today we're just going to focus on a concrete sub-goal, which is incremental type checking. And that is maintaining typing information while you're editing the program without having to retype check from scratch every time. So of course, people have thought a lot about this question. A lot of the prior work is in the implementation of language servers and compilers, incremental compilers. But a lot of that isn't necessarily written up or published anywhere. So one thing I'm particularly interested in is getting feedback from experts in this room about how that works. In terms of what has been published, of course, there's lots of work on general incremental computations or adaptive functional programming or self-adjusting computation, for example, by Umutakar. In terms of type checking in particular, there's a line of papers about translating typing rules into data log programs to which you can apply a general incremental data log solver. Similarly with a task engine, that when part of the program updates, you find which typing rules need to be reevaluated recursively. And of course, you can memoize calls to functions or type checking functions with unchanged inputs. There's also related work with respect to incrementalized browser layout computations from Utah with our collaborators that uses some of the techniques that I'll be talking about today. Okay, first of all, our particular setting, we're going to think about structural edits. So if you went to the syntax and editing session at POPL on Thursday, you'll have heard about this. But basically, we're considering changes to the abstract syntax tree of the program directly in terms of like a graph edit, a graph rewrite, hopefully local in some sense. So for example, here we have a bit of an AST for simply typed lambda calculus. The int is like a type annotation for the argument, and ask means ascription, so it's like a node representing E has type tau. And it would look in concrete syntax like you see on the left there. And a structural edit might look like this. So if you wrap this subterm in an application node, function application, it would go like this. So the binary function application then needs an argument, and we might fill that in with an expression hole leaf node. And we're interested in this partially because at Michigan, we're working on this structure editor, Hazel. But also, we can consider this just to be a convenient interface to our incremental typing theory. You can imagine using it in a different context as long as you translate, say, your text edit actions into structural edit actions. Okay, also expanding on our setting, we have some non-assumptions. So we're not explicitly modeling cursor movement. We're not assuming that edits take place some amount of time apart or some distance of space together. And the main reason we're doing that is so we can model collaborative editing, hopefully. And there was a talk earlier in the week about collaborative structure editing that this should be able to interface with. But don't worry about concurrency or commutativity or any of those concerns here. We can assume that the edit actions are linearized. We also don't assume restrictions on the program structure in terms of we don't assume the existence of files or modules or even top-level definitions. We just have one AST with all nodes treated equally, which means our incrementality has to be at the fine-grained level of AST nodes. And we don't assume a particular bound on the program size. So to elaborate on that last point, we're guided by this kind of very aspirational vision of live, massively collaborative programming. So if we imagine that there's one giant program, say the size of Wikipedia, that everyone in the world can be editing at the same time collaboratively, also like Wikipedia. And in this setting, certain approaches like retype checking the subtree rooted at an edit just won't work because that can be arbitrarily large and in fact arbitrarily wasteful because an edit that's near the top of the tree might not actually require much retype checking. Say if you make a let binding but don't actually instantiate the variable yet, you don't have to delve into the body. What we want is something more like, this is kind of abstract and I'll make it more concrete later, but working outwards from the site of the edit action and only updating exactly what needs to be updated kind of in a local way. Okay, so first of all, this is about incrementalizing something. What exactly are we incrementalizing? What's our type system? Well, a year ago at POPL'25, there was this paper on total type error localization from the Future of Programming Lab. And it introduced a formal system called the marked lambda calculus, which I will try to briefly summarize. So for example, here's one of the typing rules. And I'll break it down a little. So the first thing to notice is that it is a bidirectionally typed system, which fortunately has been discussed, I think, twice already today in this workshop. But the feature of that we'll use is that information flows locally through the AST, kind of up and down the edges in the AST. Another thing to notice is that it's not just types that are being analyzed here, but this judgment kind of takes one AST and inserts these red marks, the hot dog buns there. And those are kind of localized type errors. And because of that, in this case, that error is because this is a function application node, but the left-hand side is not a function type, as you see in the premise. And if we want to keep type checking in the presence of these localized error marks, we need to give them a type. And so we use the dynamic type from gradual typing. OK, so those are some design choices. And the main advantage they give us is summarized in this theorem, which you don't have to read. But basically, it's totality. It's that this is a total function, and that any syntactically well-formed AST can be marked in this way, just by inserting these localized type errors in a way that respects the static semantics as defined in the paper. OK, so there's an obvious way to turn that judgment into kind of an editor, which is if we start with a bare AST, E1, we can mark it, insert the marks, the local errors, into eCheck1, and then display that to the user. They can see where their errors are. And then the user can apply an action alpha to the bare AST E1, making a new AST, which can then be remarked, redisplayed ad infinitum. But the problem is when these marking stages get expensive. So naively, to remark the program, you have to traverse the entire thing linear time, and that's not going to scale as we take kind of the infinite size limit of the program. So this is exactly the kind of diagram that you're looking at when you decide to try and incrementalize something. Is there a way to go directly or more directly from eCheck1 to eCheck2? And our approach is to apply the action to eCheck1 in some modified form. And we don't directly get eCheck2, but we get something that can then step to eCheck2 according to our small step update propagation dynamics, is what we call it. So we have these two judgment forms, one that applies an action to this kind of marked up annotated program, eCheck, and one that can step these annotated programs, which kind of propagates the actions, the updates outwards from the action, and which I'll talk more about later. OK, so why do we do this? Well, one advantage is just conceptual. It kind of like lines up with the existing type system in a nice way. But also it has the practical advantage that, say we're in this case where we have a program, you apply an action, and then there's lots and lots of steps that need to happen. There's lots of updates that need to be propagated. And even in the best case, even in the most incremental case, one edit might incur arbitrarily many marks that need to be inserted. So say if you change the type of a variable that's at the top, then everywhere it's used might become a type error, and you need to take at least n steps if you change n marks. And during that time, we don't want to lock the editor for you or for your collaborators. And so by giving it the small step dynamics, you can actually jump in and keep making edits while these updates are being propagated. And we think we'll be able to prove a theorem that no matter how you interleave these actions and these update propagations, the result will always be the same. It'll always converge, and it'll always agree with what you would have gotten if you had retype checked from scratch. OK, so that's all very abstract. But now I can show you what it actually looks like on a program. So here's an AST in our simply typed lambda calculus. We also have some additional data. So on the edges, you can see the synthesized types, the up arrow. That's the inferred type at the subexpression, or the analyzed types, the down arrow, the expected type at that subexpression, or both. And we also see some marks, some localized errors. So at the x variable leaves, we find an expected bool and an inferred int. And since those don't match, we have this little red slash mark, which represents a type error, a mismatch. And we could also have errors at other locations, but we won't see that in these examples. So I'm just going to step through what these two judgments look like, applying an action and propagating the updates outwards. So say the user edits this Boolean in the surface syntax directly with an action into an int. They change it. And that's the whole action application judgment. It's it's O of 1. and we get this state. And the int has a star. And the star we can think of as a to-do for the update propagator. We can think of it as the frontier of propagation. It means it's new, but its ramifications, direct ramifications, have not been computed yet. So in this case, it's within a type. It'll just bubble up. This arrow type is new. And then we hit the ascription. And again, the left branch of the ascription is an expression. The right branch is the type that the programmer asserts this expression has. So now I'm going to show some formalism. This is the inference rule that's used to step in this particular case. It's an ascription with a new type. The ascribed type is new. And actually, let me explain the syntax a bit. Hopefully you can see that. So the important thing here is that the E expression sort has all the normal constructors, and it has locations for every possible mark or type error. But it's defined in terms of eCheck, mutually recursively. And eCheck has an E, an expression, and S, which is synthesis data, which is optionally synthesizing a type. And the type optionally is marked as new. And then it has a location for a mark to be, an error if the synthesized type doesn't match the analyzed type. And then it has an analysis data, which is like synthesized data. OK, so that's just an explanation of the syntax. And now we can apply this rule. And we see that the ascribed type is no longer new because it has been propagated to the expected type under the ascription, the synthesized type above the ascription. OK, and so now we can see where this update propagation dynamics is non-deterministic. We have two to-dos, 2 points on the frontier, and we could choose to propagate from either. But for the sake of example, let's take the lower one. We're analyzing a type against the lambda with a new expected output type. And that translates simply to a new expected type for the body of the lambda. And now our data flow path has kind of reached the end. There's a mark here because the old Boolean didn't match int. But now the rule, as shown here, says if you're at a variable and you have a new analyzed type, what you should do is think again whether these types match and update the mark accordingly. And then we're done. And indeed, they do match. And we change that type, and the user would be able to see that. And then that bit of the frontier is gone. And now I can demonstrate the interleaving of update propagation and actions. So before we propagate this to-do in the middle of the screen, let's say the user changes this int to a Boolean instead. So this one's quite interesting. So this means lambda x of type bool, and then the body. And so two things need to change when you change the annotated type on lambda. One is that the inferred type of the lambda changes. The input type is now bool, not int. But also, the inferred type of all the x's that are bound by the lambda in the body need to change. So let's just assume for now that there are pointers directly between each binding site. Sorry, those should be attached to the lambda, not the bool, to the bound variables. And we'll return to the question of how to actually maintain those pointers throughout structural edit actions. But we can assume that we can go directly from the lambda to the variables, and this is what happens. So yeah, the found type at the top of the program has changed, and the inferred type at each variable x has changed. And now we can just step through some more. So the bottom x, we reevaluate the consistency, whether the types match, they don't match anymore. And then up here, now they do match. And then we can return to our star in the middle. There's a new output type for the function that's being applied. So it's a new found type for the application. And then that's a new type for the body of the lambda. So it's a new output type for the lambda. And then we're done with this subtree. And if this were part of a larger program, we could continue to propagate. And if this is the root of the program, then the star, the frontier, kind of fizzles out, and we're done. OK, so that is a description of the local part of the scheme that kind of implements the bidirectional flow. And the only tricky part left is the context, the non-local part. So we are confronted with a problem when maintaining these binders between, maintaining these pointers between bindings and bound variables. And that is, say we insert a variable x. We have to know whether it's in the scope of, or which binder it's in the scope of. And that's kind of a non-local computation. And the obvious way to do that would be to walk the spine of the tree. You start at the x, you walk up, first lambda x you find, that's what binds it, or you hit the root. But we can't assume that the program is a balanced tree, and that could be O of n in general. So we want to do better than that. So yeah, it's hard to distinguish between these two cases without doing some heavy non-local computations. So one idea for at least checking ancestry is, say we had on each AST node an interval of numbers, such that containment of intervals corresponds to the ancestry relation in the AST. So in this case, lambda x is an ancestor of x because the range 0 to 11 contains the range 8 to 9. And then we can check ancestry efficiently by just comparing these four numbers. So that's an idea, but it raises more questions than it answers, actually. So first of all, we don't just need to check ancestry. We need to find the lowest ancestor of x of a certain form. So our plan to do that is, say we're just thinking about x, we can treat each variable independently. Every lambda x, or every binder for x in the program, we're going to put in a balanced binary search tree. And the nodes in this BST include the left endpoint of the interval and the right endpoint, and also a third number, which is the max of the right endpoints in that subtree of the BST. So here at the root, that third number is 7, because 7 is the greatest right endpoint contained in this tree. And the BST is sorted by the left endpoint. So then, just stepping through an example, say we insert an x here, and its interval is 5 to 6. So we'll start at the root of the BST and check whether x could potentially be found here by using an over-approximation of the interval. So we're not going from 1 to 4, we're going from 1 to 7. And indeed it could. And in that case, we're going to recurse right. And the reason we recurse right is because the right branch has the highest of the left endpoints, because it's sorted by left endpoint. And higher left endpoint means lower down in the tree, so better candidates. We want the tightest binder. And then we do the same check, and we find that 5 to 6 is not in the range 2 to 3, so we reject the subtree, pop back out, and now we check the direct interval found in this node, which is 1 to 4. Again, 5 to 6 is not in 1 to 4, so we're forced to recurse left. And in this case, we do find that 0 to 7 contains 5 to 6, and so we return this binding location, which is in fact the tightest binder for x in this tree. Okay, so that's one problem. But there's another problem, which is how do we actually come up with these intervals? And how do we maintain them while editing? And for that, we're going to have to go back in time to the 80s. There's this paper, 2 algorithms for maintaining order in a list, that lays out an efficient implementation of the order maintenance data structure. And I won't talk about the implementation, but I will talk about the data structure and its interface. So an order maintenance data structure has a totally ordered set of elements, and it supports the following operations. You can insert after a given element. That'll return the new element and mutate the data structure to insert it. You can delete a given element, which again mutates. And given 2 elements, you can just purely check their order in the total, their relative order. And the key thing is that all of these operations can be made logarithmic in the size, in the number of elements. So how do we exploit that? So if we go back to our original structure editing example, say we want to wrap this subtree headed with the ascription in an application, like so. Well, we can take the right endpoint of that subtree and insert 4 new elements afterwards. And yes, we're using the elements of the data structure as the endpoints of the interval. And then we can take those 4 new elements and put them in as the endpoints of our new nodes in a way that preserves our property of containment. I think there might be a bug there. Sorry. But yeah, that's, and with generalizations, we think we can apply this to other structural edit actions like deleting and moving using generalizations of the order maintenance data structure that work on batches of elements, not just single elements. Okay, so that is pretty much our plan. And now I hope we have time to talk about some of our open questions and hear from everyone here. So one open question is, how is incremental type checking approached in practical systems? And we also have a kind of technical puzzle about prioritizing the updates. So it's a non-deterministic propagation. I don't know what that thumping is. It stopped. OK. So yeah, we have multiple choices of which to-dos to propagate next. But it's much better to choose some orders than others. So if you have an upstream frontier and a downstream frontier, you want to do the upstream one first, because once it catches up to the downstream one, then you only have to do the downstream stuff once. Whereas if you do the downstream stuff, you might have to do it multiple times as different waves catch up to it. The problem is that it's not clear what the upstream order actually is, because it doesn't correspond to the AST order. Yeah. Yeah, OK. So yeah, that's like kind of a technical question that I'm not sure about. And is it possible to achieve greater incrementality? So if we imagine a case where someone keeps editing a type in the surface syntax, but without changing the expression layout, that might continue to affect, say, the presence of a type error somewhere else. But as specified here, that type would have to traverse the AST in basically the same path every time that it's changed. Is there a way to potentially remember that path and skip to the end unless the path itself changes? It seems like potentially there's room for improvement there. And related to that, can we actually use one of the generalized approaches that we discussed at the beginning to achieve a system with the same desirable properties that this one has, namely at least as incremental, and hopefully with this ability to interleave actions and updates? And that one is pretty critical, because as the size goes to infinity, then the wait time might have to go to infinity to see the effects of your actions, and you don't want to lock the editor while that's happening. But there are difficulties with kind of direct incrementalization of the process, because first of all, the information flow in the bidirectional setting is kind of nonlinear. It's not just a fold over the tree. And information through the context, it's kind of hard to tell the fine-grained data flow there. You don't want to confuse propagation through the context of one variable with another and waste time there. So yeah, I'd love to hear your thoughts on that, and I think we have plenty of time for that as well. But thanks for listening.
Questions?
Thanks for the great talk. This is really interesting. We've used order maintenance data structures, or tried to use order maintenance data structures for a totally different purpose in a type system before. It didn't end up working, but we should talk more offline about that. The actual question that I have is, at one point, when motivating this description of the problem where for which you need these BSTs of sort of all the same variables, you described sort of at the time when the user inserts the variable, when they do the edit update action, right, like right there, where you put in the x, how do you know that it's the 56x as opposed to any other numbers of x, right? Presumably the user has typed an identifier name like x. And so this may be a really dumb question, but like, why do you know which level of like, you're trying to find the 5 and the 6. That's not given to you at that point, right?
That's not a dumb question, but in the model we're thinking of, you're inserting an x at an expression hole already. So you already have like a question mark node with an interval that exists, and then it just uses the same one.
Could you explain how this BST is ordered again? I didn't really understand this bit of the presentation.
Yeah, sure. It's sorted by the left endpoint.
By the left endpoint.
0, 1, 2.
I see.
That's and that's the sorting order, and then the third number is the max above the right endpoints in the subtree of the BST.
Okay, I think I just have to like look at this slide a lot offline to understand it.
Yeah,
If
sure.
anybody else has other questions.
Hi, really nice talk. And I wonder if we could achieve that. For example, if we have a real large type, so if we edit only a part of the type, say the bool, can you switch to the type AST slide? Yeah. So for example, instead of, no, not instead of. So for example, the bool on the right-hand side of the arrow is really large, and we modify the right-hand side, or we modify the return type of. So do we need to check that the left-hand side, which is really large, to be the same as the type is propagated, or we could probably propagate the change only on the right-hand side part?
Yeah, that's a great question, and we've thought about that. So maybe we could just use Merkle trees to try and achieve like roughly constant time structural comparison. And then if you find that the thing didn't change elsewhere in the flow, you just don't continue, like the star fizzles out. But we also had this system where each type tree was accompanied with like a newness tree, which kind of mirrors the structure of the type up to some point and marks different subtrees as either new or old. And then you can, while you're like wrapping and unwrapping these trees, you can efficiently figure out whether something never changed at all. But I'm not sure that like we've completely solved that part of the problem, but that is an important consideration. Yeah.
Okay, I see. Thank you.
Mm-hmm.
Thank you for the nice talk. I guess this system, this AST-based system, error propagation system seems like it can be applied to some error fixing, error recovering system. Do you have any thoughts on that?
I guess I'm not really familiar enough with such systems to be able to comment on that. But I'd like to hear about it offline if you want to talk about it. Yeah.
The questions?
I seem to recall order maintenance is used in self-adjusting computation. Is it used in a similar way, or is this just a curious coincidence?
So as far as I understand, it's used mainly to address the second point here about prioritizing the updates. Like it maintains what is upstream of what. And when we tried to make an analogous system here, what counts as upstream in the bidirectional flow is just too unrelated to the AST, and it can switch in these non-obvious ways so that we can really figure out how to make it line up with an order maintenance structure. But I think that's how it's used. And I think the scope usage, which by the way is also used in the browser layout computations, I think it's kind of a coincidence as far as I know that they're both applicable.
Cool.
Mm-hmm.
So the vision of a Wikipedia-sized program, that is mind-bending to me. I mean, I think of an AST of some immutable data type owned by a single thread. How should I even think of that at that size? Is it some mutable data structure in a single process? Are we already talking about the compiler as a distributed program?
I'm picturing distributed, yeah, but I don't know how the details would work out. Yeah, I'm picturing it distributed, and like maybe we could have like message passing along like boundaries in the giant AST. Yeah, I mean, Cyrus has also thought about it if you want to chime in.
Yeah, makes sense. I mean, I guess it has to be at least that, yeah.
Well, like with the structure sharing. Yeah, so one thing we thought about is this appears to store copies of the types at every edge in the AST, which would naively be really big. And so we think that like structure sharing within the types, but with mutable expression trees could be a good compromise here. But then that kind of breaks the distributed picture, I think. So I'm kind of picturing like boundaries between subsystems, and within each subsystem or each like process or whatever, then there's structural sharing, but then there is duplication across these distributed subsystems.
Okay, let's thank the speaker again. And now we have another break, followed by collaboration time 2.